This title for today's session is the second quantum revolution. And the purpose of this session to me is to draw attention to what's coming. And I am especially pleased because it ties up to what I used to do almost 60 years ago. So when I was in MSc Physics, I got introduced to quantum mechanics, and then onward to computing, and who is the famous person who started much of this. And when I was in MSc, I was solving Schrodinger's equation for the hydrogen atom, for the harmonic oscillator, etc., and so on. So from that, and I remember there was a time when from my MSc to my PhD was also in something which I can relate to. My PhD was in trying to understand the behavior of solid stuff on the basis of the quantum mechanical principles. So, and that is how I got into computation, because in order to solve those equations, it was getting too complicated to solve by normal mathematical analytical techniques, so one needed to use a computer. And later on, around 1980s, Richard Feynman pointed out that if you want to understand nature in a quantum mechanical way, your classical computers will never be able. So you need to develop a quantum computer if you want to really understand nature in the quantum way that it was said. So this is why for me personally it's very interesting, and in the last few years a lot of developments have happened which have brought it from pure theoretical things. So I am a theoretical physicist doing PhD in physics, to not only practical work but to highly remunerative and profit-seeking world. So in fact now there are the programs which are written from qubits to profits. So that is the kind of a thing that was happening in London when I was in summer and so on. So the point is that this session, as you can see, this is a huge big journey. So the idea is basically to create interest, and in today's time we began with that slide of that resources are all over, and I am actually looking forward to a day a few years from now where somebody will be a well-known quantum physicist, quantum scientist, quantum technologist, and people will ask him, so where did you learn this? Did you go to IIT or TIFR? He said, no, I learned it on my own. And that is the thing that I am really looking for. So the Eklavya story repeated in the age of quantum technologies, because Eklavya did not have that many resources. Today we have a lot more resources. Only thing you need is perseverance and a strategy to learn. So this is where the thing is. I will not be doing too much of directly talking about quantum computing, because Dr. Ramesh Sharma has a proper, very good presentation with slides, etc. I am, as I was telling some people before, I have now decided that I am going to assume the role of a science commentator. You know what a cricket commentator is. He has been a cricketer once upon a time. Now he tells you about the game and what's happening and what to watch for and so on. So I am a science commentator. I've done science very closely, actively, detailed, etc. But today I'm telling you more about what's happening, where things are moving, and what is going to be exciting. I also have another very important story to share. So I said that I did my MSc, etc. I started my PhD journey around 1967 with a professor who is no more now, Professor S.K. Joshi. So Professor S.K. Joshi taught me when I was in Allahabad in BSc, then he went away to US, and by the time I finished my MSc, he came back, and he came back as a professor at Roorkee University, where he was starting a fresh new department in physics. Till then, Roorkee was an engineering college. It did not have basic departments like physics, chemistry, etc., but it was, some enlightened people said they must do that. So Professor S.K. Joshi was not the first head of the department. First head was Professor Vachaspati, but he was the immediate one, and he brought in a change. I'm telling this story because today's thing is really inspired by that. So I went with this thing, and 1967 April or so, he tells me that PhD physics is fine, you'll do physics, but go and learn computing, because the future is all about computing. And interestingly, you should appreciate the humility of a person who was then DG of CSIR, who got the Padma Shri, Padma Bhushan, Padma Vibhushan, all those things. He says, you see, I tried to learn it, but I couldn't. You are younger, you should start learning programming right now and do this thing. And I am among the first of my generation to have actually learned Fortran programming and worked on IBM 1620, IBM 7900, etc., etc. In essence, I am repeating that story to the new generation. I am saying, go ahead, learn quantum computing, quantum technologies, etc., etc. And as I was informally telling people, there is IBM Qiskit, there is this. I learned my programming from Fortran manual by McCracken. There were no books, no courses, nothing, etc. That's the stage we are in today. And the session today is basically about this. I recently saw a podcast by Bill Gates. So I am one of those in Bill Gates Notes Insider, and I recommend all of you to do that. From 26 July, he has started a few podcasts. This podcast was with Salman Khan of Khan Academy fame, and they were talking about the future of education. Again, it's very, very interesting. Our whole NEP, etc., we have no idea where the world is going. They are busy with their own thing. But so, what is interesting about that podcast from Bill Gates is, its title is Unconfuse Me. So I really like the title. The title is Unconfuse Me. He says, if you are trying to learn anything, you will first be hopelessly confused. And you're looking for somebody to unconfuse you. So the point of this session is going to be unconfusing you on quantum. Because I found that as a very good thing for everything. I mean, anything you want to learn really new, I mean, you might want to unconfuse on quantum, unconfuse on gravitation, unconfuse on black hole, unconfuse on wormhole, and whatever you want to look at. So, I want this to be, as I said, a more engaging commentary session, because from your comments, responses, etc., we'll build the conversation further. To get started, I will show you two videos. One video, the first video, is a video announcing the National Quantum Mission. So, the Government of India, it talked about quantum some 2 years ago, pre-COVID days. They had announced some budget, etc., but then they slept for 2.5 years. Now in April, again they have woken up and announced a National Quantum Mission with some 6,000 crores over 8 years or whatever. And the director NPL, in fact NPL is our metrology standards body. The director of NPL was recently in Moscow in some conference. He has made some announcement that in August there will be a framework of this kind of thing which will be coming up. So watch out, any time news you will get some framework for it. But I can informally say this, although this is being broadcast, I don't really care. See, eventually they will copy from somewhere and give you something. So far what they have copied is from the UK quantum thing. The UK said we will have 4 missions, they said 4 hubs, etc., etc. So they are almost cut copy paste from what UK has been doing for the last 10 years or so. And this thing. The other is in the traditional style, they are trying to say that India is the 7th country to do in this quantum, etc., and so on. And their whole thing is about building a quantum computer. And as you will see in the national mission, they say in the next 8 years, they will build something like 1,000 qubit processor, which will be a great achievement. IBM has already announced Osprey with 433 qubits long ago, and they have announced a 1,000,000 qubit processor, etc., etc. But the idea is to. The other thing, and why I am making this commentary is very important, because see, the National Quantum Mission, we should be seen as something where even the government has understood the importance of quantum. but they're completely lost. They have no idea of what the world is like, because the whole obsession is with creating a quantum computer. Now, any one of you who has said any IT industry knows that the hardware is the least important thing. It comes software, the operating system, the user interface, and how you will work. And these people are still with great problem. We will make a 1,000-qubit quantum computer in 8 years, as if it is a very big thing. But the point is that is not so. What I am saying is there is going to be a reason I am going to is that if I make this from a restricted thing to the Government of India, the IIT, the TIFR, the IIC Bangalore, and so on, with 7-8 institutes they are looking at, let them do their work. Very good, we'll clap for them. But to me, the future is about quantum computing among the masses. Steve Jobs did not make any new technology himself. Everything you have in the iPhone was pre-existing. He just put it together. MP3 player was before that, GPS was before that, everything. There's nothing Steve Jobs has invented specifically, but he created the iPhone. The point today is going to be the application, usage, etc. on that. And this is why I want this to be a massive thing. So when people get to know, but they will think of completely new ways and new problems that can be solved. What happens with traditional scientists, and I am part of that breed, is they see certain thing which has been there. So this is a problem for 10, spend my next 10 years trying to solve this problem, and they will solve it. But in the meantime, people who are outside your space have figured out many new things. And purpose of this session is to basically do that. And equally to say that we are not just talking wishy-washy in the air, we will have serious stuff. So Ramesh Sharma will go through quantum computing in great detail. I think we have somebody who will talk about quantum biology and other things that will come around. So let me begin with the first video. And in these videos, we will see a part of it together, and then we'll say you can see the rest of it. I'll give some comments.
Hello and welcome to The Print. I'm Mona Basu, Assistant Editor at The Print. And today we are going to talk about the quantum mission that was announced by the Cabinet just yesterday, Wednesday this week. And what exactly this mission is, what it encompasses, and what we can expect from it in the future, that's what we are here to discuss today. And with me, I have Dr. Akhilesh Gupta, and he is the Senior Advisor at the Department of Science and Technology, and he is the one heading this mission. And he is going to tell us exactly what it is. What is quantum? This is something that a lot of people are struggling to really understand. When we say quantum computing, what are we talking about? What is quantum?
Well, if you ask me what is quantum, I think if you heard that the classical mechanics and the quantum mechanics, the difference has been that, if you recall a very famous de Broglie theorem, it says that every particle, whether small or big, has a dual character. One is the particle, and another character is the wave.
Right.
Where everything inside all of us generate wave.
Right.
But larger the size of the particle, smaller is the wave.
Mm-hmm.
At the quantum level, the size of the an atom is nearly 300 crore smaller than the human being. So at that level, the wave size is larger than the particle size.
Right.
That is all quantum mechanism, where it shows that any particle, and just give you a very good example of quantum. The light, when the light is coming to you, you think that it is, what do you think? And your reaction is that it is an electromagnetic wave.
Right.
It is an electromagnetic wave, but then this light is full of photons,
Yes.
particles.
So it capitalizes on the dual nature.
Duality of the particle and the wave nature.
Right, right. So, where and how does this fall into with when we talk about computing? What is the difference that we see when we are talking about classic?
So I want to give some comments. Now those of you who know, and he's smiling already, you realize that he has no idea what it is. Absolutely, well, this is amazing. He's the head. They are announcing he is the head of the mission. 6,000 crores he's going to spend. He has absolutely no idea. And what is more interesting is that he is head of a big department of DST. किसी से लिखवा लेता, teleprompter से बोल देता कि भाई क्या है. It is not only is ignorant, he is also completely irresponsible. He has no sense. He has no sense that and this is a big national video release, right? And with the journalist has studied more. As you will see, the journalist has studied more about this than he has. And you should have said that if you are head of this mission, you would have a 3-line statement to say what the mission is, which will attract everybody. See, this is what we are told, get your best lines first, right? And I will later on also say, but I can't resist. There's a very nice book today by Michio Kaku on quantum supremacy. He tells you how this will change the world. Climate change will be solved, cancer will be cured, this will be done, that will be done, all kinds of things. But here, because I am a physics teacher, I realize from his school days, वो quantum physics के नाम से डरता था. I was beginning with classical quantum physics. And everything he is saying is wrong. So let me also put a bit of that in context and then we'll move so further. Suddenly says de Broglie, etc. Now all of you remember when we study school for the first time, light is a ray. Geometrical optics is what you first study. You don't study that light is an electromagnetic wave first. You first study light is a ray of light. You do all kinds of geometric optics, convex lenses, focus, 1 upon f, 1 upon f1 plus 1 upon f2, this, that, whatever. Only when and reflection, refraction, total reflection, etc. Only when you go up to class 11, 12, that you start talking about the wave nature of light, which was Huygens theory, and then you see interference, diffraction, and so on. So you see the wave nature of light. Interestingly, the tragedy is that Newton had observed the wave nature of light in something what is called Newton's rings, and we do that at school level. But because he had this belief of particle theory, he would create very convoluted things to explain that, because he used it accept Huygens wave theory, etc. So, in the case of light itself, people had understood that there was one way of describing as particles and rays, and the other as waves, and so on. Then something interesting happened, that they thought that light has this behavior. Then a person called Thomson, he did an experiment where he identified electron and proved that electrons are particles, and he got a Nobel Prize for that. His son Thomson did another experiment and proved that electrons are waves. He just got the interference pattern, he also got a Nobel Prize. And de Broglie said it is neither particle nor wave, he also got a Nobel Prize. So there's a lot of kind of story that we then started realizing that wave and particle, and actually if you get serious enough by then, you will realize that the particle has some behavior. Wave, particle, matrix, probability, wave distribution, all these are ways of expressing something. It's not the same thing. When you say it's a Schrodinger equation, then it's a probability, wave of probability of the particle being somewhere, and so on. So the point I was trying to say is that these also, his mindset is quantum, very small, an atom. But there are what are called macroscopic quantum effects also. Superconductivity is a macroscopic quantum effect. Superfluidity is a macroscopic quantum effect. And he also thinks that in this lab, atomism, but yet that plant that you have outside, doing photosynthesis is a quantum machine. Because photosynthesis is happening at room temperature, at this thing, even at hot temperature like 40 degrees, it is doing that. So the difficulty, and this is where it is important to understand that they have no idea of what it all involves. And what is interesting is that he is not trying to even respond to the question, but what is quantum? Quantum of what? Now, people with physics know that it's quantum of action that is being talked about. And if that action is of the order of what is called Planck's constant h 6.6 and 10.7, then quantum features start manifesting itself, and so on. But I just wanted to say this, that two things. One, that even the government wants to do it. Second, that it has a huge impact because it is actually the true way of describing nature. Now, as we get to appreciate that, and this is where the challenges are. So, since I've been a physicist, even finding the quantum structure of a hydrogen atom is difficult, helium atom becomes very difficult, and if you have anything with one of the basic examples they give is caffeine in coffee, it's very difficult to calculate that from what is called ab initio or first principles. So, we'll go to the next part of this. And listen to this very carefully. He was talking of waves. Here is wave of
So again, let me go to the basic.
Sorry.
So when the computers were discovered, and that includes
Computers were not discovered.
your mobile. Your mobile is also a computer. Your calculator. This was the first computer inside. So the discovery of this computer were based on the binary digits, bits, 0 and 1. So all digits were in the combination of 0 and 1. I'll just give example. If it is, you have to write 1. So in the 4 digits, you write 0, 0, 0, 1. If you write 2, 0, 0, 1, 1, and so on. So
अब आप में से सबको पता होगा ना कि 1 1 to 3 हो जाता है. Now you see, this is what is amazing. He is a public television. I mean, he doesn't care. And उसमें मैं यही सोचता हूँ, I have been forwarded this link to a lot of people without any comments. These comments are private. So I was basically reminded of that. वो एक गाना होता ना, समझने वाले समझ गए, जो ना समझे वो अनाड़ी है. तो समझने वाले तो समझ गए कि this is the leader of the National Quantum Mission. So we'll carry on for a few minutes and then we'll leave it.
every computer cannot recognize digits, 20, 25, and all these digits. It recognizes bits.
Right.
So the bits are being used for all computations.
So that is what we
That is what the conventional computers read.
Right.
But when it comes to quantum bits, it is the superposition of 0 and 1. That is, if suppose there is a 0 and a 1, you have crores of stages or states between 0 and 1.
थोड़ा सा रोक लीजिए.
Which means,
See, now between and 0 1 is a fraction. It is not a superposition. Superposition is two vectors, super or whatever. And between 0 and 1, they are all fractions expressed as decimal. हाँ बताइए.
What he said that the computers are based on binary is wrong.
हाँ
It's wrong in the sense, much before this binary system came in vogue, the concept of computer was there.
हाँ
The only thing the 0 1s were come in, we could not get a physical device which could have two stable states of 0 and 1. In early 70s or mid 70s, lot of work was done on ternary logic. That is where 3 states are there. People, lot of literature came. I also contributed at the time. कि अब वो मिल नहीं रही थी हमें कोई डिवाइस जिसमें 3 स्टेजेस हों, तो उससे और छोटा हो जाता है कंप्यूटर. एक्चुअली बाइनरी की बजाय एनरी हम कहते थे उस समय. वो सारा मैथमेटिक्स अवेलेबल है एंड राइट फ्रॉम 30s, आज से नहीं है. कंप्यूटर का जितना मैथमेटिक्स अवेलेबल था पहले से अवेलेबल. The only thing is the physical system did not was not there. That's
very good. And you have absolutely raised a very good thing, because that is the challenge about quantum computing. That जिसको qubit कहते हैं वो बनेगा कैसे. And now, so that is exactly, so now you imagine arithmetic, he doesn't know. Base, he doesn't know कि base 10 होता है, base 2 होता है, base 8 हो सकता है, base 3 हो सकता है, जो भी आप चाहो. Logarithms, he doesn't know. Slide rule में उसको करते हैं, he doesn't know. And as Professor Suresh Chandra has said, see, when the mathematics of things to different bases, etc., has been there have been devices of doing calculations fast. Napier's tables and the slide rule, which all engineers use, were calculating devices. And in between, there were devices which are called analog computers, which are based on LCR circuit. Because the equation for an LCR circuit is the second order differential equation. Therefore, by adjusting LCR, you could get the answer of that equation, looking at the current and voltage. Digital became interesting because we could get that kind of a thing about gates and being able to represent and move on. And this is the challenge of quantum computing. So the first thing about quantum computing is that if you want to represent a superposition of 0 and 1, how would you manifest it? And हाँ
हमने एनालॉग कंप्यूटर की बात करें, उस समय उसकी डिफरेंशियल इक्वेशंस could only be solved with the help of analog computers.
Correct.
Whereas digital computer, there was used to be a what you call program, sub-program, which will take a lot of time.
हाँ
Then we started talking of hybrid computers.
Right.
That part of the equation will be solved by the analog computer, and part of it will be done by the digital computer. But fortunately or unfortunately, you may say, the speed of digital computer became so much that the concept of a hybrid computer, where analog computers and the digital computers had to work in
right.
coordination, was
Keep up with the accuracy. When you wanted measurement to a large.
जरूरत नहीं महसूस हुई.
हाँ, correct, exactly.
Now the
In fact, the new generation doesn't even know that there was an analog computer. Similarly, your grandchildren will not know there was a traditional computer.
IT कानून में बड़े अच्छे analog computer हुआ है.
हाँ
It could be programmed incident.
नहीं वो इतना ही नहीं है अभी तो there's not time. There was a stage in progression when hydraulics was being used for computing. All calculations were done. हाँ
In chemical industry,
correct. So
वो जो है, you have a NAND gates with the
correct. तो वो
so that the concept that is chances of spark are minimized. I don't
Right.
know it's still that
Huh.
there or not, but there was a concept.
Right, that's what I'm saying. So my point was just that trying to say that when this is opened up, lot more things will come because people will respond, and our task is to make this accessible to lot more people. See, the official task, and I have no hesitation, I've been part of that IIT privileged group, but they will keep it only for 100 students will be taught quantum computing, they will be taught qubit by this kind of a person, and that is good. Whereas what I am saying is, in today's time, let us spread it out, and people can come up with completely new things, and that's the idea. So next, a little bit more.
That is a superposition taking place between the 0 state and the 1 state.
Right.
In the physical space, let me tell you what is 0 and 1 space. So in the atom, you have one orbit, and then another orbit, and then another orbit. When the electron moves from one orbit to another orbit, it leaves some energy.
Right.
That energy is the photonic energy,
Right.
photon, and that also has the wave energy. So it is that energy that is actually represented in the case of quantum.
Right.
So in quantum, instead of bits, it is qubits.
Yes.
That is quantum bits, where the energy between one state and another state is being represented through superposition of those two states.
Right.
So he talked about wave, and my reaction was wave was stupidity coming from him. So you can watch this video at leisure at your whenever. I just wanted to tell you that we should treat this as government's acceptance that this is there, but no further, because beyond that there's. But before I leave, I also want to show you another interesting video. And आप शुरू कर दें उसका ना. This is by.
Hi, my name's Talia Gershon, and I'm a scientist at IBM Research.
Yeah, एक minute.
Today I've been
Let me
challenged.
give that. So this is a professional and IBM Quantum, etc. And this video is very interesting because it is trying to explain quantum computing at 5 different levels. One to a school-going child, one to a teenager, one to a graduate student, one to a professor, and one to a serious professor of theoretical physics. And why it is very interesting is that you will see now the difference in communication. वो head है सबका ये, and you will see that she is also going to explain superposition and qubits to small children, and in a much more interesting kind of a way. And what I am interested in is that we need to do the same thing to be able to get everybody to start appreciate this in some sense and be curious to know more. So the idea is get interested and curious to know more. Our problem with our bureaucracy is, and I have no hesitation in saying that we try to show we are doing something great and this is all beyond you. That is the message that they are trying to say. But I am very optimistic because I've been all over. Fortunately, I have a very good combination of being in IIT Kanpur and in IGNOU. So I know that you can have a set of combination where many people can get access to something which is otherwise made exclusive. So I will not make much comments of this. We'll watch this and then we'll move on. हाँ.
In 70 or 71, there was a question in Lok Sabha about the computer in IIT Delhi. At that time, one Professor Chaturvedi from civil engineering, he was in charge of the computer. So the younger people at the lecturer level, they were asked to write a small note of the question answer. They said that at that time it had only 64 kilobytes of memory, and each word was 24 bits. तो उन्होंने कहा जी 64 किलोबाइट की मेमोरी. प्रोफेसर चतुर्वेदी जी ने अपना एक और उसमें डाल दी. उसने कहा 64 किलोबाइट means, but it's mean that it has, the computer is made of 64,000 bits. That is components. कि उन computers का इतने
टुकड़े हो गए.
computer बना हुआ. He also did not know what computer is, and that answer was read in the Lok Sabha.
हाँ.
ऐसा चलता है.
नहीं वो तो सी मेरे को आई हैव नो प्रॉब्लम विथ लोकसभा, राज्यसभा, सुप्रीम कोर्ट. आई टेल यू इन नहीं देखिए सुप्रीम कोर्ट में जब 2G का मुकदमा चल रहा था, पूरे डिस्कशन के बीच में एक जज दूसरे से कहता पर ये स्पेक्ट्रम होता क्या है. So let's see this. You'll enjoy this.
To explain a topic with 5 levels of increasing complexity. It's a completely different kind of computing called quantum computing. Quantum computers approach solving problems in a fundamentally new way. And we hope that by taking this new approach to computation, we'll be able to start exploring some problems that we could never solve any other way. Hopefully by the end of today, everyone can leave this discussion understanding quantum computing at some level.
What's this?
Yeah, what do you think that is?
Fancy chandelier.
I think so too. We jokingly call it the chandelier. That's real gold, you know. This is a quantum computer.
It's a quantum.
Yeah, it's a really special kind of computer.
What does it do?
It calculates things, but in a totally different way to how your computer calculates things. What do you think this is?
A,
Yeah? Do you know what your computer thinks that is?
0, 1.
This really specific combination of zeros and ones. Everything that your computer does, showing you Pink Panther videos on YouTube, calculating things, searching the internet, it does all of that with a really specific combination of zeros and ones, which is crazy, right? That would be like saying your computer only understands these quarters. For each quarter, you need to tell it that you're going to use heads, tails, and you assign it heads or tails. So I can switch between heads and tails, and I can switch the zeros and ones in my computer so that it represents what I want it to represent, like an A. And with quantum computers, we have new rules we get to use too. We can actually spin one of our quarters. So it doesn't have to choose just one or the other.
Can computers help you with your homework, your really hard homework?
Yes, Yeah, that can, especially if doing your homework involves calculating something or finding information. But what if your homework was to discover something totally new? A lot of those discovery questions are much harder to solve using the computers we have today. So the reason we're building these kinds of computers is because we think that maybe one day they're going to do a lot of really important things, like help us understand nature better, maybe help us create new medicines to help people. What's your favorite kind of computer? Smartphone, tablet, regular, laptop, PC?
I've got to go with my iPhone.
So what do you do with your iPhone?
Social media, use it for studying
Have you ever run out of space on your iPhone?
all the time.
Me too.
Yeah, always when I'm trying to take a photo.
So did you know that there's certain kinds of problems that computers sort of run out of space almost? Like you're trying to solve the problem, and just like how you run out of space on your iPhone when you're trying to take a picture, if you're trying to solve the problem, you just run out of space. And even if you have the world's biggest supercomputer, did you know that can still happen?
Wow.
So my team is working on building new kinds of computers altogether, ones that operate by a totally different set of rules. So do you know what that is?
I have no clue.
It's a quantum computer.
A what?
Have you ever heard of a quantum computer?
I haven't.
Have you ever heard of the word quantum?
No.
Okay, so quantum mechanics is a branch of science, just like any other branch of science. It's a branch of physics. It's the study of things that are either really, really small, really, really well isolated, or really, really cold. And this particular branch of science is something we're using to totally reimagine how computing works. So we're building totally new kinds of computers based on the laws of quantum mechanics. That's what a quantum computer is. I'm going to start by telling you about something called superposition. So I'm going to explain it using this giant penny.
Wow. Is that like worth 100 pennies?
I don't know what it's worth, but I can put it face up, right? And that's heads. I can put it face down, right? So at any given time, point in time, if I ask you, is my penny heads or tails, probably you could answer it, right?
Yeah.
Okay, but what if I spin the penny? So let's do it. Okay, so while it's spinning, is it heads or tails?
Heads.
While it's spinning,
Oh, I would know.
it's sort of a combination of heads and
Yeah,
tails,
yeah.
right? Would you say? So superposition is this idea that my penny is not just either heads or tails. It's in this state which is a combination of heads and tails. And this quantum property is something that we can have in real physical objects in the world. So that's superposition. And the second thing that we'll talk about is called entanglement. So now I'm going to give you a penny. When we use the word entangled in everyday language, what do we mean?
That someone's intertwined or...
Exactly, that there's two things that are connected in some way, and usually we can separate them again.
Yeah.
If your hair is tangled or whatever, you can unentangle it, right?
Yeah.
But in the quantum world, when we entangle things, they're really now connected, and it's much, much harder to separate them again. So using the same analogy, we spin our pennies, and eventually they both stop, right? And when they stop, it's either heads or tails, right? So in my case, I got tails and you got heads. You see how they're totally disconnected from each other, right? Our pennies in the real world. Now, if our pennies were entangled and we both spun them together, right? When we stop them, if you measured your penny to be a head, I would measure my penny to be a head. And if you measured your penny to be a tails, I would measure my penny to be a tails. If we measured it at exactly the same time, we would still find that they were both exactly correlated.
That's crazy.
It's so cool, right?
Oh my god.
The way that we are able to actually see these quantum properties is by making our quantum chips really, really cold. So that's what this is all about, actually. This is called a dilution refrigerator, and it's a refrigerator. It doesn't look like a normal refrigerator, right? But it's something that we use, actually there's usually a case around it, to cool our quantum chips down cold enough that we can create superpositions and we can entangle qubits, and the information isn't lost to the environment.
Like, what could those chips be used to do?
So one of the things that we're trying to use quantum computers to do is simulating chemical bonding. Use a quantum system to model a quantum system.
Yeah, I mean, I'm definitely going to impress all my friends when I tell them about this. They're going to be like, quantum what?
So what do you think that thing is?
Is it some sort of conductor circuit?
That is a really good guess. There's parts of that that are definitely about conducting. This is the inside of a quantum computer.
Oh, wow.
Yeah, this whole infrastructure is all about creating levels that get progressively colder as you go from top to bottom down to the quantum chip, which is how we actually control the state of the qubits.
Oh, wow. So when you say colder, you mean like physically colder?
Yeah, like physically colder. So room temperature is 300 Kelvin. As you get down all the way to the bottom of the fridge, it's at 10 millikelvin.
Oh, wow.
Yeah. Amanda, what do you study?
So I'm studying computer science, currently a sophomore, and the track that I'm in is the intelligent systems track. Machine learning, artificial intelligence.
You ever heard of quantum computing?
From my understanding, with a quantum computer, rather than using transistors, is using spins. You can have superposition of spins, so different states. More combinations means more memory.
So that's pretty good. So you mentioned superposition, but you can also use other quantum properties like entanglement. Have you heard of entanglement?
I have not.
Okay, so it's this idea that you have two objects, and when you entangle them together, they become connected.
Oh, okay.
And then they're sort of permanently connected to each other, and they behave in ways that are sort of a system now. So superposition is one quantum property that we use, entanglement is another quantum property, and a third is interference. How much do you know about interference?
Not much.
Okay, so how do noise-canceling headphones work?
They read like ambient wavelengths and then produce like the opposite one to cancel out.
They create interference. So you can have constructive interference and you can have destructive interference. If you have constructive interference, you have amplitudes, wave amplitudes that add, and so the signal gets larger. And if you have destructive interference, the amplitudes cancel. By using a property like interference, we can control quantum states and amplify the kinds of signals that are towards the right answer and then cancel the types of signals that are leading to the wrong answer. So given that you know that we're trying to use superposition, entanglement, and interference for computation, how do you think we build these computers?
I have no idea.
So step one is you need to be able to have an object or physical device, we call it a qubit or quantum bit, that can actually handle those things, can actually be put into superpositions of states. You know, two qubit states that you can physically entangle with each other. That's not really trivial, right? Things in our classical world, you can't really entangle things in our classical world so easily. We need to use devices where they can support a quantum state and we can manipulate that quantum state. Atoms, ions, and in our case, superconducting qubits. We make qubits out of superconducting materials.
But as like a programmer, how would quantum computing affect a different way of writing a program?
It's a perfect question. I mean, it's very early for quantum computing, but we're building assembly languages. We're building layers of abstraction that are going to get you to a point as a programmer where you can interchangeably be programming something the way that you already do and then make calls to a quantum computer so that you can bring it in when it makes sense. We're not envisioning quantum computers completely replacing classical computers anytime soon. We think that quantum computing is going to be used to accelerate the kinds of things that are really hard for classical machines.
So what exactly are some of those problems?
Simulating nature is something that's really hard because if you take something like, you know, modeling atomic bonding and electronic orbital overlap, instead of now writing out a giant summation over many terms, you try and actually mimic the system you're trying to simulate directly on a quantum computer, which we can do for chemistry. And we're looking at ways of doing that for other types of things. There's a lot of exciting research right now on machine learning, trying to use quantum systems to accelerate machine learning problems.
So would it be like in 5 years or 10 years that I would be able to have like one of these sitting in my laptop just in my dorm?
I don't think you're going to have one in your dorm room anytime soon, but you'll have access to one. There's 3 free quantum computers that are all sitting in this lab here that anyone in the world can access through the cloud.
Okay, so quantum computing creates new possibilities and new ways to approach problems that classical computers have difficulty doing.
Couldn't have said it better myself.
So I'm a first-year master's student, and I'm studying machine learning. So it's in the computer science department, but it mixes computer science with math and probability and statistics.
So have you come up upon sort of any limits to machine learning?
Certainly, depending on the complexity of your model, then computational speed is one thing.
I have colleagues here that tell me it can take up to weeks to train certain neural networks, right?
Sure, yeah.
And actually, machine learning is one research direction where we're really hoping that we're going to find key parts of the machine learning computation that can be sped up using quantum computing.
Yeah, it's exciting. So in a classical computer, you know, you have all sorts of logical gates that perform operations and they change an input to some sort of output, but I guess it's not immediately obvious how you do that with quantum computers.
If you think about even just classical information like bits, right? At the end of the day, when you store a bit in your hard drive, there's a magnetic domain and you have a magnetic polarization, right?
Sure.
You can change the magnetization to be pointing up or pointing down, right? Quantum systems, we're still manipulating a device and changing the quantum state of that device. You can imagine if it's a spin, that you could have spin up and spin down, but you can also, if you isolate it enough, you can have a superposition of up and down.
Sure.
So what we do when we try to solve problems with a quantum computer is we encode parts of the problem we're trying to solve into a complex quantum state. And then we manipulate that state to drive it towards what will eventually represent the solution.
So how do we actually encode it to start with?
Yeah, that's a really good question. This actually is a model of the inside of one of our quantum computers.
Okay.
So you need a chip with qubits. Each qubit is a carrier of quantum information, and the way we control the state of that qubit is using microwave pulses. We send them all the way down these cables, and we've calibrated these microwave pulses so that we know exactly this kind of pulse with this frequency and this duration will put the qubit into superposition, or will flip the state of the qubit from 0 to 1. Or if we apply a microwave pulse between two qubits, we can entangle them.
How do we measure
Yes, exactly, also through microwave signals.
it? Okay.
The key is to come up with algorithms where the result is deterministic.
Interesting. So what do those algorithms look like?
There's sort of two main classes of quantum algorithms. There's algorithms which were developed for decades, right? Things like Shor's algorithm, which is for factoring, Grover's algorithm for unstructured search, and these algorithms were designed assuming that you had a perfect fault-tolerant quantum computer, which is many decades away. So we're currently in a phase where we're exploring what can we do with these near-term quantum computers. And the answer is going to be, well, we need different kinds of algorithms to really even explore that question.
Yeah, certainly having a search algorithm is very useful. Factoring, those are definitely useful things that I would imagine could be done a lot faster on a quantum computer.
Yeah, they also unfortunately require fault tolerance. Right now, the algorithms that we know of today to do those things on a quantum computer require you to have millions of error-corrected qubits. Today we're at like 50. It's actually amazing that we're at 50. There's things that we know or we have strong reason to believe are going to be faster to do on a quantum computer. And then there's things that we'll discover just by virtue of having one.
Sure. How could someone like me who's a grad student get involved in this, or what kinds of challenges are you facing that someone like me could help out with?
I'm glad you're interested. I think the place where lots of people can get involved right now is by going and trying it out and thinking about what they could do with it. There's a lot of opportunity to find these near-term applications that are only going to be found by trying things out.
I'm a theoretical physicist. I started out in condensed matter theory, the theory that studies superconductors and magnets, and I had to learn a new field of quantum optics and apply those ideas. One of the nice things about being a theorist is you get to keep learning new things.
So Steve, tell me about your research and the work you've been doing in quantum computing.
My main focus right now is quantum error correction and trying to understand this concept of fault tolerance, which everybody thinks they know it when they see it, but nobody in the quantum case can precisely define it.
It's something that we've already figured out for classical computing. Like, something that amazes me is all the parallels between what we're going through now for quantum computing and what we went through for classical computing.
I was asking a computer scientist recently where to read about fault tolerance in classical computing. He said, oh, they don't teach that in computer science classes anymore because the hardware has become so reliable. In a quantum system, when you look at it or make measurements, it can change in a way that's beyond your control. We have the following task: build a nearly perfect computer out of a whole bunch of imperfect parts.
Common myth. How many qubits do you have? That's the only thing that matters. Like, just add more qubits. What's the big deal? Pattern them on your chip.
The great power of a quantum computer is also its Achilles heel, that it's very, very sensitive to perturbations and noise and environmental effects. You're just multiplying your problems if all you're doing is adding qubits.
Exactly. So I think something that frustrates a lot of people about quantum computing is the concept of decoherence, right? You can only keep your information quantum for so long, right? And that limits how many operations you can do in a row before you lose your information.
That's the challenge, I would say. As much progress as we've made, it's a frustration to still be facing it.
Let's talk about some of the things we think need to happen between now and fully fault-tolerant quantum computers to get us to that reality. I mean, there's so many things that need to happen. In my mind, one of the things we need to do is build all these different layers of abstraction that make it easier for programmers to come in and just enter at the ground level, you know?
Yeah, exactly. So I think there's going to be a kind of co-evolution of the hardware and the software up here and the sort of middleware and the whole stack.
Another common myth. In the next 5 years, quantum computing will solve climate change, cancer, right?
Right. In the next 5 years, there'll be tremendous progress in the field, but people really have to understand that we're either at the vacuum tube or transistor stage. We're trying to invent the integrated circuit and scale up. It's still very, very, very early in the development of the field.
One last myth I think we should bust, Steve. Quantum computers are on the verge of breaking into your bank account and breaking encryption and cryptography.
There does exist an algorithm, Shor's algorithm, which has been proven mathematically that if you had a large enough quantum computer, you could find the prime factors of large numbers, the basis of the RSA encryption. It's the most commonly used thing on the internet. First, we're far away from being able to have a quantum computer big enough to execute Shor's algorithm on that scale. Second, there are plenty of other encryption schemes that don't use factoring, and I don't think anybody has to be concerned at the moment. And in the end, quantum mechanics goes to the side of privacy enhancement. If you have a quantum communication channel, you can encode information and send it through there, and it's provably secure based on the laws of physics.
You know, now that everybody around the world can access a quantum computer through the cloud, people are doing all kinds of cool things. They're building games. We've seen the emergence of quantum games, right? What do you think people want to do with them?
I have no idea what people are going to end up using them for. I mean, if you had gone back 30 years and handed somebody an iPhone, they would have called you a wizard. So things are going to happen that we just can't foresee.
So I hope you enjoyed that foray into the field of quantum computing. I know I've personally...
Stop it. So I just wanted to share this with you because it shows you degrees of communication and the excitement. And what was most inspiring for me is the look of enthusiasm on that old physics professor. I am also... हाँ मैं वो इसीलिए दिखा तो मुझे भी can this thing. And the few comments that I want to make before we request Dr. Ramesh Sharma to make a more systematic, it gives you a whole glimpse of the situation, the challenges, and this thing. Some things which I specifically want to point out, because it goes there in passing, is the name of Love Grover. Now, in quantum computing, there are two algorithms which are famous. One is Shor's algorithm, done by Peter Shor, and the other is Love Grover algorithm. Peter Shor's algorithm is about factorization of a very large number. Most of us know that RSA is based on the idea that you multiply two large numbers, two large prime numbers, and you get a bigger number. If you want to factorize this, it is almost impossible. That is what all our security is based on. Peter Shor's algorithm, when the quantum computer is invented, will be able to break that, and all RSA thing, all blockchain, all crypto, everything will get affected. So that is one part. Love Grover's algorithm is for database search in a large database using quantum algorithms. So the reason I am saying this is because, again, I want to emphasize that I see the potential in India of people creating new quantum algorithms. People who have a mathematical trend, computer science, they may not see a quantum computer at all, but they know this is how quantum computing works and this is how we can do. One important transition point is, while other things may be difficult, but when the first thing that we'll see is the appearance of quantum machine learning. So if you recall, AI progressed because the chips got better and better. Till we had only traditional CPUs, AI was again a theoretical thing, expert system, rule-based expert systems, etc. But we didn't get anything practical out of it. But when they realized they can use graphical processing unit to do some of the calculations, machine learning progressed. then people like Google started creating TensorFlow and Tensor Processing Unit. So tomorrow's model, the first model to be, I think, quantum aware would be, you have a large model on machine learning. You would have used your CPU, GPU, TPU so far. Now you can send the problem to some QPU, which may be with IBM, this, that, whatever. Get that done, get back to yourself and move on. So to me, the adoption of computing, quantum computing will be first in this kind of a thing. Another interesting part that is coming up with respect to Shor's algorithm is that people are worried that when this quantum computer actually comes, and even if it comes in very limited garage kind of a thing or something secretive, and that person can break down all the security systems of everything. So people are even thinking that there are people who are collecting all the data which they can then decrypt once it is available, and the phrase for this is Y2Q. So Y2K was the year when things would break down because of that 2K thing, etc. So this is the day quantum computer becomes real, not necessarily publicized. Somewhere somebody has got it, all the crooks will reach there, and Y2Q will be something which is going to be very interesting. So what I'll do is, okay, I can reserve that comment for later. So we'll now request Ramesh Sharma to talk at length properly about quantum computing in a series of presentation. After that, we have somebody who will do this on quantum biology and related stuff, and then I'll do some wrapping up, etc. and so on. Take it, sir. All yours. कितना टाइम है अभी?
अभी 11:20 हुए हैं।
हाँ,
टी ब्रेक।
तो आप टी ब्रेक कर लेते हैं, तो टी ब्रेक के बाद शुरू करिए। I think they have enough. We can have a tea break and then just do it. ठीक?
So let's have a little break. Let's go to the
क्या हुआ? अरे चाय पी लीजिए फिर इंट्रोडक्शन में
लगभग 1:30 बजे के आसपास। हाँ ठीक है, यस। साउंड अच्छा वो तो उसमें जाएगा, ठीक है। So okay friends, welcome back, and let us continue to learn about quantum computing. And I request Pansar that please keep adding your commentary because there are few things which are I have tried to keep it non-technical in nature, so that, but there are certain terms where and like particularly when Steve, the last person, the professor there, he was talking about certain properties of quantum mechanics and quantum computing, they come in there. So because it is still such an area where the general understanding about this topic is not clear to the people. And as we have discussed in our previous sessions here, that sometimes the people think that if they are studying something, how it is going to be useful to them. Like in school education, when we are in the school, we study so many subjects, but then we don't understand that what is the value of that to in our either real life or in our later life. So let us begin with the thing that how these phenomenon they are being used in our daily life, and these are some of the examples where the phenomena of quantum works in these are based on the principles there, but we may not be aware of it. Say LED lights, the light emitting diode there, and then the laser printer, how the quanta, the packet, it converts that the light source, and then when it hits the drum, the roller, the toner from there, it gets printed on the paper working there. And similarly the LCD monitors also, and particularly when the advisor to the government means his knowledge of physics we have already seen, even about the chemistry. When the electrons and protons which are there in they go from a lower state to the higher state, the energy is released when they come to the natural state, not while going up they release the energy. It is contrary when they return to their neutral state, because they can't keep on be in the higher excited state, we call it in chemistry, in chemical bonding or atomic structure and like that. That is the phase when the energy is released. So this is there. Similarly in refrigerators, a common usage of that, and then this glass, this is a new application of this, that and particularly if you see many of the high-rise buildings, this is made of sand, which is silicon, and silicon is used in making of these chips, and particularly during the pandemic time, the automobile industry, it was heavily suffered because of the lockdown. The chips were not being used, and then every vehicle, they are there nowadays, so many of the things currently, so that, and then the fibers in there. So these are some of the areas in which the quantum is used. We may not be aware of it directly, that how it goes. So let's understand that what is quantum computing. And as you have already seen in that video, these computers, they are completely different from the traditional kind of computers. To see the impact of quantum computing, a very common example is that these traditional kind of computers which we have with us, either as a laptop or the desktop, when you install any software, most of the times, depending on our operating system as well, so it asks two questions basically, that what is your system, whether it is 32-bit or 64-bit, depending on that you install the software. Mostly the software which is meant for 32-bit will work in 64-bit environment as well. But if it is the higher one and the machine is 32-bit, it may have certain challenges while running it. And then the second aspect is that what is your operating system, whether it is Windows based or Macintosh, iOS or Linux environment, and that kind of thing from there. So here this machine is only 32-bit or 64-bit in traditional sense, whatever we are using. But there, like particularly the Facebook, when they have created their quantum computer, it has these the so-called bits in millions, and it occupies lot of space. A huge kind of infrastructure is created with that.
Google's quantum computer, Sycamore, did something that's going to break your brain. Once again, it achieved quantum supremacy by performing a calculation within a few seconds that Frontier, the most powerful supercomputer in the world, would take 47 years to complete. This is something similar to what Google did in 2019 with 53 qubits. But this time, Sycamore performed the task with 70 qubits. Qubits are the quantum equivalents of classical bits that can represent 1 or 0, or both at the same time, potentially allowing for certain calculations to be performed at astonishing speeds. Quantum computers are still in their early stages of development, but the progress that Google has made with Sycamore is a major step forward for quantum computing. It shows that these machines are becoming more powerful and capable, and it suggests that they could soon be used to solve real-world problems. To get regular technological updates, follow The Secrets of the Universe.
So basically the advantage here is, as we said, that why we use computers. The traditional computers, they are basically for information processing. We like there is some input and then we wait for the output to solve a problem or to process some information, to process some data. That is the traditional kinds of thing, because a normal person, as a layman, our requirement is that only. But then comes the higher level, where we need to study about our environment. It involves lot of data, complex kind of data, and for that we need a special kind of machine, which is not possible through these traditional lower level computing devices. For that we go with like supercomputers, mainframe computers and other things. These machines, they are used for solving the real world problems, in which like study of weather, or like in that earlier video you saw the discovery of new drugs, or because they involve lot of computation, and that power is possible using these things there. So let us see about how this thing developed, and it is believed that the first one, as you already know about Richard Feynman, believed that he was the first in 1982. His paper was published in Springer, Simulating Physics with Computers. There, that suggested a certain sort of a quantum computing device to be used as a high power. But otherwise, this is graphic is a little smaller, but in the early 90s up to there, slowly the work is being processed when we had the D wave or the quantum wave there, and then the Microsoft, Google, IBM, etc., these other companies, they also started working on that. One of the reason behind is that every day lot of data means is getting generated. So we have so many devices, we have so many as in the field of IoT, the Internet of Things. There are two basic things in IoT. One is the sensor and another is actuator. Even the simple kind of this microphone, it has they have the sensors. So like in simple terms, this microphone through sensors, it is capturing the voice and then converting that voice in them, and then the actuator. So like if you see, we have a water tank on the ground or underground water tank, and we have to uplift the water on the overhead tank. So the sensors, they check that whether water level has fallen below a certain level or above a certain level. So that is the work of the sensor. But alone sensor doesn't help us. The sensor has to send a signal to the actuator to either switch on the water pump or switch off the water pump. And there are so many things in which these things work, like capturing the data and then processing it with the other. So that is the field of sensors and actuators. They work in many of the areas from there. So
we have a system at my home where I don't switch on or switch off the motor. There is a timer which switches on, seeing the water level in the tank, and when it is full, it switches off automatically. And this is for last 10 years.
Yes, sir. Because it makes, like you see the water taps nowadays in the public installations. We don't need to touch the tap. We just block the light. So the sensors, the sensors are of various kinds, like acoustic, which work on the sound, then the light based, then the movement based, and like on the basis of that, the sensor captures some signal, converts it, and sends the message to the actuator to work on something. So like how the tap flow should start, or the siren should blow out if there is some unauthorized movement, like in the security cameras, vision based, or those kind of things. So this brings us to this question, that how these quantum computers, they are different from classical computers. And as has been explained, that in classical computing, it's basically the 0 state and the 1 state, whereas in quantum computing, we have the in-between state as well. And this is again the Shor's algorithm for the quantum, where finding the prime factors of an integer, and long back it was developed by mathematician Peter Shor. So that algorithm is the basis of in how to deal with to generate on a massive larger scale for that.
In the fast-paced world of technology, it's no surprise that new advancements are being made every day. But what is truly groundbreaking is the convergence of two of the most exciting fields of research: quantum computing and artificial intelligence. This collaboration is poised to bring about a new era of technological advancement, and the future looks brighter than ever. Artificial intelligence has been making great strides in recent years, with the development of artificial intelligence chips to support the growing demand for smart products and technologies. The artificial intelligence chip market is booming, and countries like China are launching national plans to support development and manage associated risks. This has led to a surge in investment in artificial intelligence startups, with established tech giants and innovative startups alike competing to make their mark in the artificial intelligence chip market. But while artificial intelligence is already making a huge impact, it's the potential of quantum computing that truly has experts buzzing with excitement. IBM's System 1 is a quantum computer that is capable of completing certain tasks with a speed that surpasses laptops by millions of times. This is just the tip of the iceberg, as quantum computing is set to revolutionize the field of artificial intelligence through better algorithm training, with the potential to solve complex problems in areas such as mathematics, science, and even climate change and food security. It's no wonder asset management firms are early adopters, and commercial use is soon to follow. Quantum computing is different from traditional computing in that it uses qubits that can exist in multiple states instead of binary bits. This capability opens up a world of possibilities, but also presents new challenges, particularly in the realm of cryptography. That's why countries like the US and China are investing in mastering the technology for national security purposes. Quantum computing has been referred to as the beginning of the internet, classical computing, and even a new industrial revolution. Its development presents a world of opportunities and challenges for society. and scientists are working tirelessly to make quantum computing more stable and usable for practical purposes. President Biden recognizes the significance of quantum computing and toured IBM's Quantum Data Center in 2021, calling it vital to our economy and equally important to our national security. So, hold on tight and get ready to be transported to a future where the impossible becomes possible.
This is a very important point in it, and if you remember the interview of Professor Steve, he also said that the traditional classical computers, they are stable now, the hardware, the software, basically that field has been stabilized. But in quantum computing, it is still the phase, and that's why there is a term which it will come in the next slides. It is called as error correction, to bring out the stability in that. So now there are certain fundamentals to this field of quantum computing. The three major of them are superposition, entanglement, and measurement uncertainty. And this is the famous experiment. In superimposition, as she was demonstrating, the coin, head, tail, or in between those states. And this has been explained, Pansar also in the last few sessions has been explained, that the cat in a box, unless you open the box, you do not know whether the cat is alive or dead, that state. So this is...
You've heard about quantum entangled particles, where I can create a pair of particles that know about one another, and now they're separated in space and in time. And if you observe that other particle, it instantly changes the state of the particle back, the other particle that's back where I am. And by the way, that they communicate instantaneously, faster than the speed of light.
When you say if you observe, but you have to do something.
Yeah, you have to do, yes.
So something has to interact with it, it's not woo.
The problem is the word observe, people think is a psychological thing, but in physics, it's got nothing to do with...
measurement.
It's a measurement thing.
Right.
And so in other words, if there's an electron sitting in the middle of this table and all the lights are out, I can say, I think there's an electron here, let me find out. And the moment I turn on the lights, the light interacts, a photon interacts with the electron and kicks it somewhere else. So the more I try to measure its position, the less I know its position. Ooh.
So here the point, it says that, and particularly a few years ago, this became a very important... The more I know about the location, the less I know about it. Means there is... इसलिए आपकी जरूरत है उसको ठीक लाइन में लाने की।
वो उस तरफ आप जाएंगे तो हम आपको फिर पूरा कर सकते हैं। जाती रही भावना जैसे प्रभु मोर देखी वैसे। वो दृष्टा पे निर्भर हो रहा है। नहीं, but you are absolutely right. So so let me make some comments here. First, this entanglement is a very difficult thing to accept, and no less than Einstein was in complete disagreement with it. उनका एक बड़ा famous paper निकला था. So quantum mechanics is a very interesting field. There are, let's say, 20 names who are all things, unlike many others where there is one person responsible for it. Newton's law, Archimedes' principle. Quantum, there is no one person. Max Born, Max Planck, William Heisenberg, Schrödinger, Dirac, Einstein, and they fought with each other. So Einstein got the Nobel Prize for photoelectric effect, but he criticized quantum mechanics by writing a very famous paper, you can Google for it, called the EPR paradox. In 1935 he said quantum mechanics is bakwas. There is some hidden variable inside which is telling where it should go. And because it was written with Einstein and Podolsky and Rosenberg, the war chal gaya. Then the mathematician John Bell came, and he said that if there are hidden variables, then this should happen. That's called the Bell's equation inequality. And demonstration by experiment, it was proved that Bell was right and Einstein was wrong. And this was done as recently as 2022. 2022, the Nobel Prize was given for establishing quantum entanglement and in a sense proving Einstein wrong. And the people who got that prize, for years their colleagues would say, क्या बकवास कर रहे हो, ये कैसे हो सकता है, वो कैसे हो सकता है, and so on and so forth. So you are absolutely right. The point is that we are now trying to say that see, all of us know that seeing is not believing, right? Metaphor. And very interestingly, so you also have an idea of law. I come from a law background. In law, the eyewitness was the most important person. Chashmudid Gawah. In science, that eyewitness is considered irrelevant. It's the instrument which is considered right. उसने क्या देखा हमें कोई नहीं जाता है. So this is what the thing. Similarly, our conceptualization. Now again back to that thing. अगर आपको पता है हमारे गीता में ये वो विश्व रूप दर्शन की बात करते हैं, कहते हैं इस आंखों से नहीं दिखेगा. You need, so same thing is the problem with quantum. See, having grown up in this world, you tend to say particle या wave या ये या वो, but ये है ही कुछ और चीज. And you haven't seen anything yet because now in frontiers of physics, they're talking of 11-dimensional, 14-dimensional world, जिसमें हम लोग रह रहे हैं. हम लोग 3 dimension में comfortable हैं. और आपने अगर recent physics भी पढ़ी होगी, तो you would have heard of 4 basic forces: gravitation, electromagnetism, the strong interaction, and the weak interaction. People at Fermilab have just announced the possibility of a 5th force. They've looked at some forces on muons, which are 400 times heavier than the electrons, and found they have some wobbling which is not explained by the standard physics. Correct, exactly. So the point is, we are exploring completely new frontiers, and it is extremely difficult for people, if you are constrained by what you have, to accept that. So therefore the idea is, keep looking at the data, the experiment, the observation, the explanation, and that is why we always say, this is the thing of today. See, एक समय एरिस्टोटल एकदम ठीक था, फिर न्यूटन ठीक था, फिर आइंस्टाइन ठीक था, फिर आइंस्टाइन भी गलत हो गया. तो हम लोग किसी व्यक्ति पे नहीं जाते हैं, हम जाते हैं आज हमारा अंडरस्टैंडिंग, उसमें कॉमनली अग्रीड अंडरस्टैंडिंग. सो दिस इज वेयर द थिंग इज. Since I've been given a chance to talk, I'll share a couple of other things. When he talked about sensors, it's very interesting that जब तक सेंसर लैब में है तब तक एक कहानी है. सेंसर मार्केट में आते ही कहानियाँ बदल जाती हैं. There's a very famous story, and आप अभी भी गूगल कर लेंगे. अटलांटा जॉर्जिया में एक कॉन्फ्रेंस हुआ, बड़ा भारी. उसके कुछ डेलीगेट्स जब गए वहाँ पे वॉशरूम में, तो ऐसे हाथ डाला तो पानी नहीं निकला, सोप नहीं निकला, सोप डिस्पेंसर. तो इंटरनेट में टाइटल है, द रेशियली बायस सोप डिस्पेंसर, दिस दैट व्हाटएवर, खूब जैसे लोगों को मजा आता है. फिर द मैरियट होटल ने कहा कि भाई हम क्यों रेशियली बायस करेंगे, हमारे तो सब कस्टमर हैं. इट टर्न्ड आउट कि वेरियस वेराइटीज ऑफ सेंसर, उस आदमी ने जो सेंसर वहाँ लगाया, इंस्टेड ऑफ मोशन सेंसर लाइट डिटेक्शन सेंसर लगा दिया. वो सस्ता पड़ा होगा. तो अब लाइट डिटेक्शन सेंसर में गोरे आदमियों की तो रिफ्लेक्शन ठीक आ रही थी, काले के समय बुझाओ हो जाए. So this was a very big thing. So this is where, when technology touches humans, you have to be a bit more careful. One more quick story before we get back. And my request to all of you is, if you can find out ways of explaining why a quantum computer is so much more effective, it would be a very good thing, because so far nobody is able to explain that well enough. Bit, qubit, wave, but it doesn't explain why it becomes faster. Now, and he used the term quantum supremacy, which Google achieved for the first time. So John Preskill is a professor at Caltech. उन्होंने ये term use किया था, quantum supremacy, by trying to say this is a stage at which a quantum computer will do some task which no classical computer can do. And Google ने ये किया, but that was an artificially created task. It's not one of the natural problems of the world. But I want to draw an analogy. The distance of the sun to the earth, average distance, is 93 million miles. The speed of light is 180,000 miles per second. So the standard question, what time does it take for light to come from the surface of the sun to the surface of the earth? Interior of the sun to the surface is another thing in nuclear physics, takes millions of years. But from the surface of the sun to the surface of the earth, how much time does it take? So you say 93,186,000, you divide, you get 200 seconds and therefore 8 minutes, 20 seconds. Very good. We could do this in our head. Now try to do this without using what was called by the rest of the world the Hindu numeral system. What was their system? The Roman number system. Use the Roman number system, try to write 93 million, try to write 186,000. There is no cancellation of zeros there. So you have to keep on subtracting in Roman arithmetic 500 times if you can do it and have the patience to do it to get the answer. And that is why for a long time in the Western world, the Hindu numerals were suspected upon. They thought there is some magic in it, some mantra in it, that they can do it so fast in their head when we can't even do on reams and reams of paper. They accepted our number system only after it was called Hindu-Arabic number system. Till Hindu, they were very, very afraid. Now, this is the metaphor for classical and quantum computing. The quantum computing uses processes which are very different. Now, detail engineering is different. But the idea is it is no question of faster and faster computer of the traditional type. You can do as fast as you want Roman arithmetic, but you will not be able to do astronomical calculations. And that is why India was so ahead in astronomy. We could calculate the eclipse, we could calculate this, all the movement of the star, because we had that system. The same hope is from quantum. When quantum is able to solve many problems which we traditionally cannot solve, they will be solved, and that is where the big hope is. We'll get on more and more, continue with the story.
And in continuation with this, about quantum entanglement, what he was saying, this is related to quantum measurement and uncertainty, like the Heisenberg principle, which states that we cannot know both the position and the speed of a particle. So that's what. If you know the position, then it will be difficult to get the speed or vice versa of a particle. And this
Hello and welcome to our channel. Today we're going to talk about 3 different types of quantum computers: superconducting qubit, ion trap, and topological qubit. Make sure to hit that like button, subscribe, and turn on notifications to stay updated with our latest content. Superconducting qubit quantum computers are one of the most common and promising types of quantum computers being developed today. These quantum computers use a superconducting material, such as aluminum or niobium, to create qubits that can represent quantum information. The qubits are cooled to extremely low temperatures, near absolute zero, and operated with very low electrical resistance to minimize errors and decoherence. Some examples of superconducting qubit quantum computers include the Google Quantum Computer and the IBM Quantum Computer.
So this is how the architecture they try to create, like as he said, superconducting by Google and the others. Then we have quantum dot by HRL Laboratories, and then electron on helium by Euroc, or neutral atoms in optical by Atom Computing, called Quanta, and like that. So the various kind of architecture is being planned, that how we can tap the power of these systems.
Computers of all kinds may experience hardware failures in addition to bugs and hacking. Microchips used in modern computers are relatively robust and fail only in extreme circumstances. Each data bit used in digital devices consists of hundreds of electrons or photons traveling through electrical wires or optical fibers. So if some of them are lost, there are plenty left to deliver the information to the next point. Unlike digital devices, quantum computers rely on single particles to represent their qubits. If a qubit is lost, this means an immediate error. A quantum quantum particle, be it an electron or a photon, is extremely sensitive to its surroundings. Any noise in the environment will destroy its quantum coherence. How can we keep many of them in sync, or maintain coherence between many quantum particles to build a real quantum computer? Here is how. Think about a donut. This geometrical object is also called a torus. We can securely tie a loop through a hole, which will remain no matter how the torus is deformed. Unlike a flat surface or a sphere, where a loop can easily collapse under a small change. In quantum computing, we can build logical qubits out of many particles instead of one. The quantum information is then shared amongst the many particles. To keep overall coherence, they need to be carefully pinned using specific topologies, such as a torus. This can create more robust qubits because the shape keeps them orderly arranged. Such a qubit can recover from losses and is more robust to external noise, mitigating errors and maintaining coherence. To make quantum computing an everyday reality, both algorithms and physical devices should be robust.
So again, this is here is that because the stability in these systems is yet to be achieved. To work on that, the phenomenon of this error correction, it is inbuilt for that. And this is also related to the phenomenon of quantum, in which we study about the superposition or the states of coherence. Coherence means in how these the particles they work with each other. And to understand the phenomenon of quantum interference and decoherence, see this. Atom can be at two positions at the same time, and the ability of superposition to state any quantum particles, a molecule or a photon or a spin. So the energy level, it cannot be so when you measure it, only one of the two states is observed randomly. The energy level there. So the time it takes for superposition to disappear is called as the decoherence time, and this is crucial for quantum computing. Okay, so now the current state of quantum technology, as you see that many of the big corporations, they are spending huge amount into the kind of algorithms development. In fact, there are certain websites which provide the algorithm. The traditional kind of algorithms, they don't have many variations into it, but the quantum algorithms, they have more variations into it in terms of the result outputs from there. So there are certain fields which are emerging as the basis of the new developments in quantum field.
I'm going to explain quantum mechanics in 60 seconds. Light was originally theorized to be a particle by Sir Isaac Newton, until a scientist by the name of Thomas Young hit the scene with his famous double-slit experiment. What Thomas Young did was he took a light and he shined it through two small slits. Now what was expected to happen is that light particles would shine through these slits and create two splotches on the screen. What actually happened is there was some strange pattern that appeared on the screen. This was because light was actually showing wave-like characteristics instead of particle-like characteristics. But according to...
So it says that the experiment was done that there is a two holes slit was there, and if we put the light, technically it should produce only two impressions there, but it was found that it's not the case, and it's a kind of a wave. In reality, what it happens from
scientists at the time, all waves have to have a medium. I mean, ocean waves travel through water, sound waves travel through the air. So how do light waves travel then? Well, for a long time, scientists hypothesized this invisible medium known as the luminiferous aether, also called the ether. This ether was a hypothetical invisible medium that existed everywhere on Earth and in space that light could travel through. However, multiple experiments were ran to show that the ether actually did not exist. It wasn't until the discovery of electromagnetic waves and Einstein's work on the photoelectric effect that showed us that light can behave both as a particle and an electromagnetic wave that requires no medium to travel through.
So quantum mechanics now deals with the examination of the behavior of matter and energy, both at the atomic level and at the subatomic level. The another field is quantum computing, which is basically processing the data at a much faster speed with the help of the improved algorithms. Another area which is coming is this quantum information science. So this is basically the quantum key generator, which is quite important here in that, and particularly it has its applications in cryptography for the security of the systems in that, and this is how it generates the various keys and which are used for information safety in that. Another branch which is emerging is quantum optics. If you remember the interview of Professor Steve, the last person who was there, he was saying that I am working on quantum optics. The quantum optics is like how the light and matter they interact in the quantum regime, and to understand that, let's see this video. Coming up as the quantum chemistry, which is how to understand the behavior of atoms and molecules. for computational chemistry. So like in catalysis, photo-induced charge transfer, and material sciences, the property of to understand the behavior of atoms and molecules, how they interact with. Then
quantum biology is a field of science which is an intersection between biology and quantum mechanics. Quantum biology can explain many biological mechanisms and phenomena that cannot be explained by most of biological principles. The phenomena such as Hall plans and heart.
So I'm skipping this. The next is the material science.
Throughout history, people have searched for new materials using chemistry, physics, and engineering. Today, we live in a world infused with technology. From computers and smartphones to airplane design and healthcare, all of these advances have been possible because of our ability to discover the properties of materials in new ways. Understanding and creating new materials is at the forefront of tackling the challenges of the future.
At Lockheed Martin, we try to use materials sciences in ways that benefit our customers. We might be looking for light but strong materials that would help us build better aircraft, or for materials that would help us protect our spacecraft in harsh environments that are not on this planet. The primary difficulty in discovery of new materials and analysis of existing materials is the complexity of those systems and the computational muscle that would need to be brought to bear to analyze them completely.
Physicists have long predicted the role of quantum computing in simulating new states of matter. The behaviors of materials are governed by the laws of quantum physics, and understanding the quantum nature of materials is key to finding novel ways of exploiting their properties for new technological advances. D-Wave has taken the significant step of demonstrating two separate examples of simulating quantum materials during phase transitions on a quantum computer.
This experiment is really validating the original conception of quantum computing, which was to simulate the physics of many body systems that are really difficult to simulate classically. And so I think a lot of people are going to be excited about this. What we've done is we've provided a quantum simulation of kind of a complex lattice of qubits or spins, and we're showing that we can program our computer to simulate this, and it's really fast.
When we have this direct capability to do programmable experiments and to simulate this quantum piece of matter, we can pursue complicated simulations. We can seek to understand very complicated phenomena.
I think this is the beginning of an era that quantum computers start helping us understand materials, and hopefully in the future they can help us design new materials. And designing new materials could mean designing new drugs to cure cancer, or designing new materials for batteries, which are very important for future of our planet Earth. And in many other applications, they may help us.
Personally, I'm excited about material simulation because it's a chance to poke nature in ways that we have not had a chance to do it before. Right? I'm an engineer, but my inner physicist would love to access the tiny pieces of the world and see how they're behaving and build up our simulations from first principles.
Feynman's original vision for quantum computing was based on the idea that we would want to use quantum computers as simulators for very small systems that we have a very hard time simulating with classical means. And I think that this experiment shows that we're on the verge of being able to do that.
So similarly, this leads the study of like superconductivity or quantum phase transitions. There is another field where we study the behavior of matter in condensed phases. So the property of say liquids, solids or other complex states. So that has resulted into a quantum condensed matter physics.
Condensed matter physics is a branch of physics that deals with the physical properties of condensed phases of matter.
Condensed matter physicists seek to understand the behavior of these phases by using well-established physical laws. In particular, these include the laws of quantum mechanics, electromagnetism, and statistical mechanics.
And then since we study the quantum mechanics, there are its relations with having an understanding of the particle physics there. So this gives rise to the quantum field theory.
दोस्तों क्वांटम थ्योरी के मुताबिक हमारा यूनिवर्स इलेक्ट्रॉन, क्वार्क और न्यूट्रिनो से मिलकर बना है, यानी कि हमारे यूनिवर्स में सबसे छोटे पार्टिकल यही हैं, इनसे छोटा कुछ भी नहीं हो सकता। पर क्या ये थ्योरी सच में सही है? जी नहीं, हमारा यूनिवर्स सिर्फ 3 ही चीजों से बना हुआ नहीं हो सकता है, और साथ ही साथ हमें इस थ्योरी से ये भी पता नहीं चलता है कि अलग अलग फोर्सेस किस तरह काम करती हैं और क्वार्क और इलेक्ट्रॉन किससे मिलकर बने हैं। इन सभी प्रश्नों के उत्तर हमें क्वांटम फील्ड थ्योरी देती है। दरअसल क्वांटम फील्ड थ्योरी के मुताबिक क्वार्क जैसे अन्य पार्टिकल वाइब्रेशन है, और वह भी अपनी अपनी फील्ड में। जैसे ग्रेविटी स्पेस टाइम फील्ड में एक कर्वेचर जनरेट करती है, जिसकी वजह से ग्रेविटी अपना प्रभाव डाल पाती है। ठीक इसी तरह हमारे यूनिवर्स में कुल 16 फील्ड मौजूद हैं, 12 मैटर की और 4 फोर्सेस की फील्ड हैं। इन्हीं फील्ड में वाइब्रेशन की वजह से पार्टिकल का निर्माण होता है। जैसे इलेक्ट्रॉन फील्ड में वाइब्रेशन की वजह से इलेक्ट्रॉन का निर्माण होगा। दोस्तों क्वांटम फील्ड थ्योरी आज तक की इंसानों के द्वारा बनाई गई बेस्ट थ्योरी है, जो कि पूरे यूनिवर्स को एक्सप्लेन कर पाती है।
And then, as you said that here in it, and Einstein and others like Newton, they also worked on the one of the most interesting phenomenon of our planets and others is the gravity. We are stable now on this planet due to the phenomenon of gravity, and the field which is related to this is quantum gravity, where we try to combine the knowledge of quantum mechanics and the general relativity for that. So let's see that.
Quantum gravity is the hardest problem in physics. It's the attempt to unify the 2 pillars of modern physics, quantum mechanics and general relativity. It's the study of how gravity works at the quantum level, where the laws of physics are very different from what we experience in everyday life. One of the biggest challenges in quantum gravity is that gravity is the weakest force in nature. It's so weak that it's impossible to study for particles in the lab. We can only see its effects on very large objects, like planets and stars. Scientists have been working on quantum gravity for decades, but they haven't been able to come up with a complete theory. So it remains one of the biggest unsolved mysteries in physics, one that scientists are determined to solve. For more videos of Cosmos in a Minute, follow the secrets of the universe.
So, and this has impact on certain which is related to our real life, and particularly the field of timekeeping and navigation. As you know that due to the globalization, our movement, it has increased a lot. And then very recently, I think it was the last year something, there was that time correction in the atomic clock. It was being discussed that we need to adjust some microseconds into the time clock. So this is on the global scale, the timekeeping and a kind of a navigation pattern, it becomes very much important. And that has given rise to the field of quantum metrology.
Quantum metrology is an emerging field that harnesses the principles of quantum mechanics to improve the precision of measurement by exploiting the unique properties of quantum systems such as entanglement and superposition. Quantum metrology can enhance the accuracy of measurements of physical quantities such as time. This has potential applications in fields ranging from fundamental physics to medical imaging, where high precision quantum metrology is still in its early stages, but its potential to revolutionize measurement technology has generated significant interest in this.
And as just now we were discussing about sensors, these play a very important role in our daily lives. And then there are the impact of those certain things like magnetic fields or gravitational waves or temperature on sensors. So the quantum sensing is the field which deals with those
Sensors are essential for animals and humans to survive. Who can see, taste, smell, hear, and touch.
Hey!
Machines and computers can also detect their environment, but they do not use eyes, nose, or ears for this, but sensors. Sensors that measure with quanta are currently being developed. They can measure much more precisely than conventional sensors. How do they work? Quanta are super sensitive. They are quickly affected by air, sound, light, or magnetic fields. Because they are so sensitive, they can measure tiny changes, making them extremely precise. The tricky part is shielding the quanta from any influences that shouldn't be measured. And it is not at all easy to measure the behavior of the quanta without affecting them through the measurement itself. Researchers have come up with various methods for this. In one variant, a single quantum is imprisoned in a diamond. This means that the quantum is always in the same place and protected from external influences. This makes it easier to measure even the smallest changes. But why all this? Quantum sensors could soon be used to measure the magnetic field at a location so accurately that gas and water pipes could be detected underground.
Yay!
And that's just by making tiny changes in the magnetic field and no drilling at all. Likewise, minerals or underground caves could be found, or archaeological discoveries could be made. But measurements in our bodies will also become much more accurate, thanks to quantum sensors. Brain activity could soon be measured so accurately that prostheses, for example, could be controlled by thought alone. Quantum sensors have many other applications. Researchers are working to determine the position of airplanes, submarines and satellites with quantum sensors. A GPS system may soon be able to measure where we are to the millimeter using quantum sensors. These sensors are still only in the test phase and are still being further developed, but soon quantum sensors could change our lives on Earth.
Okay, and then this is bringing another change in like the imaging field, in which we use imaging applications for that. Particularly if you see initially in the earlier days when the X-ray was the only option for the doctors to see what is inside. But then it doesn't make any big analysis, because the X-rays they are only the bones, but the muscles and some other. So then the other kind of devices came. Currently the quantum imaging is a field where the improved resolution and the applications they are being developed.
Imagine you want to take an image with light that never interacted with the object. Sounds like magic, but we make it happen here at Fraunhofer IOF in Jena, Germany. We achieve this by harnessing the non-classical quantum properties of light, especially entangled and correlated photon pairs. A photon is the smallest portion of light. Generating them as pairs, the pair itself becomes one quantum object, meaning that a photon magically knows what happens to its twin partner. Exactly this property of entangled photon pairs is utilized for our quantum imaging with undetected photons. Our first object is this little happy face. A pump laser goes through a nonlinear crystal and generates photon pairs. The two photons are spatially separated, one interacts with the sample, whereas the other one is going to the camera. Based on the pair's correlations and an interference effect, the object appears on the camera, although the incoming light never interacted with the object. What we like the most about this approach is that both photons can have different wavelengths, meaning different color. One can be optimized for highly efficient detection, the other for the interaction with the sample. This is of particular interest for biological systems, especially photosensitive samples. A lot of cell components are modified or even die when they are eliminated with too much light of the wrong wavelength. So the fundamental principle behind this phenomenon was first demonstrated by the Zeilinger group at ECOCI in Vienna. Our job here at the Quantum Enhanced Imaging Group at Fraunhofer IOF is now to transfer this approach into real-life applications. So we are going to build the next generations of microscopes, quantum microscopes.
And then Professor Suresh is here, his field, like the machine learning field. So this is quantum machine learning, the field, where the exploration of quantum algorithms as well as the development of new models for machine learning tasks is being created for certain complex computations.
Hello and welcome. Quantum computers have been making a rapid progress over the last 2 or 3 years, and they are becoming useful for a couple of tasks. And one of the tasks that we are looking at solving with the quantum computers is a couple of challenges in machine learning. So machine learning has also been making rapid advances. For instance, in deep learning, we have very large neural networks which can solve, for instance, classification problems very effectively. In fact, these deep learning networks are relatively simple to do on classical computers by using parallel resources. So this is an easy problem, and there's no point in solving this problem with a quantum computer. So quantum machine learning is mainly about finding difficult models in machine learning, for instance, probabilistic models over graph structures that resist calculations on classical computers. That's the main pitch for quantum machine learning, and this course is very practical. So we are not only looking at abstract algorithms for which we need perfect quantum computers, we also consider the quantum computers that we have today that interact with the environment and they perform imperfect calculations. Moreover, everything in the course is going to be implemented in Python, in Jupyter notebooks. So by the end of the course, you yourself will be.
So there. And then we need to study the connections between the quantum information and thermodynamics. So this brings us to the quantum thermodynamics.
Welcome to today's episode of Quantum Thermodynamics. In today's episode, we will dive into the fascinating world of quantum thermodynamics and explore its implications in the field of physics. Make sure to hit that like button, subscribe, and turn on notifications to stay updated with our latest content. Quantum thermodynamics combines the laws of quantum mechanics and thermodynamics. Thermodynamics deals with the transfer of energy and heat to different systems, while quantum mechanics deals with the behavior of matter and energy at a very small scale. Quantum thermodynamics strives to reconcile the discrepancies between the two fields and provides a better understanding of energy transfer at a molecular and atomic level. One of the most interesting findings of quantum thermodynamics is the concept of work extraction. It was previously believed that extracting work from a single heat reservoir was impossible, but quantum thermodynamics has challenged this notion. This is because of the concept of quantum coherence, where wave-like behavior of particles can be observed. We can exploit this concept to extract work from a single heat reservoir. Another fascinating concept of quantum thermodynamics is the Carnot limit. The Carnot limit is a theoretical limit on the efficiency of engines, which is based on the second law of thermodynamics. Quantum thermodynamics has shown that quantum fluctuations can decrease the efficiency of engines, which means that the Carnot limit can be surpassed by designing engines that employ quantum coherence. Quantum thermodynamics has a wide range of applications, including the development of more efficient solar cells, cooling systems, and quantum computers. In conclusion, quantum thermodynamics is an exciting field that seeks to bridge the gap between quantum mechanics and thermodynamics. It has provided us with a better understanding of energy transfer at the atomic and molecular level, and its implications are far-reaching, from more efficient solar cells to the development of quantum computers. Thank you for watching today's episode of Quantum
Okay, so let us see some of the use cases. Some I showed you in the beginning, where like refrigerator or laser printer or optical fibers and some. But on a technical side, it had its uses, particularly like in quantum communication or secure cryptography, because of the basis of the algorithms involved in it, which are quite of the complex and advanced level. Then the uses are in quantum sensing, as you have seen that, like this is the imaging to the body, and the quantum 3D endoscopes which are being developed there. Similarly, now as you know that very recently through ISRO we have sent, and many of the countries they keep sending satellites. There is very important, in fact on our mobile phones also, it's a piece of hardware, it is called as gyro sensor. And similarly in the field, the quantum gyroscope for satellite stability, because if it gets disturbed, whole of the exercise can go waste. Millions of the amount which has gone into that, it can go. So for precision measurements and other things, it has a very important application for that. The another one which is related to us is based on the principle of annealing for quantum enhanced AI and machine learning. This is quite interesting, that the principles like guessing to find out the shortest, particularly for the travel industry, and when the airlines they have to make arrangements of and particularly for logistics or for transport, means the companies which work on a global scale, how to minimize the distance and narrow it down to particularly. So those kind of simulations to find out those things, the quantum field is very much helpful for that. We have seen the applications in many other areas, but what about education? And for that there are the work is going on by various organizations which are working for quantum computing in education, like Microsoft, they have come up with certain programs, particularly through their fault tolerant quantum machine to Azure their environment for that. And similarly, some of the institutions, they are integrating quantum concepts into their curriculum. This is IBM Quantum, the educators program, and there you can also register yourself by providing it, and then they can allow you the access for that. Then we have this quantum simulation for scientific research. This is a website, it is called as aglassert.com, where you can use these examples for basically like in electronics and other things, like so quantum teleportation or super dense coding, symmetry breaking, quantum Fourier transformation, like that. Those they work with that. There is another website which you can use is Quantum Inspire. They have a lot of interesting resources for educators where you can run your own quantum algorithms. So because you need your own IDE and other environments where you can work and you can test your algorithm. So this website provides a space for us. And similarly, we have to enhance the equity and inclusion in education using quantum computing. The reason is that we need to bridge the gap, and Pansar just very recently in one of his blog captured the term as quantum divide. So we need to bridge that quantum divide in that. And another issue which is this is Cointelegraph platform, where you can find out the interesting articles and information on this field. But one thing another has been noticed is about inclusivity is the representation, particularly like women in quantum. It's a quite thing, because we have it has been found that the gender and the racial gaps in quantum field, it's also quite interesting. So the question here is that can reskilling help satisfy quantum's workforce requirements? And particularly like Zeno is here, the next slide is maybe for quite important for him, that how we can use quantum computing for students with disabilities, how we can make them more accessible. So this is Scientific American, an article by Dario Gil on increasing the testing of quantum computing techniques, and they will open the door for solving new kind of problems with that. There are certain education initiatives and resources which are available for teachers, particularly like Quantum Computing Outreach Program, Q Open Source Foundation. This foundation, it provides certain codes, evaluation techniques, mentorship programs are there where the teachers and the teams, they can make in there. In addition to that, there are certain online quantum learning platforms which are available, particularly like this is Azure of Microsoft. There they also provide you quantum development kit and optimization, quantum computing algorithms where you can build your own apps and run testing for them. And similarly, and I don't know when they will wake up now, but it is good that CBSE in the past woke up and suggested that include AI from class 8 to 12th. But then what we need is quantum computing even for K-12 sectors. So this is the website like qsoft.org, a research center for quantum software, where we have different kind of applications and other information for school sector. Similarly, there are certain national supported, this is from United States, the q12education.org, which is National Q12 Education Partnership, where people, the schools, institutions, they can come together and can, work in tandem to solve and include the quantum learning tools and inspire the next generation of quantum leaders for that. But still there are certain challenges and barriers to equity, because this is one of the big area where the access is a big issue. And this is a good site, it is Querica, where they provide quantum resources and carriers like access, training for that, and those facilities. You can see the map where the things they are being used. So we need to have our educators prepared for teaching the quantum concepts, and this website, Quantum Learning Education, it also offers various in level 1 for embracing quantum learning, and it's committed to its implementation. Then the level 2 is there, where we demonstrate the competence by purposefully facilitating the quantum learning systems and strategies. And then the level 3 is there, where artfully orchestrate the quantum learning systems for the desired results to solve the real world problems into that. So what is a need is that to overcome the socio-economic and cultural barriers, because this is still a challenge. And then so we have the let us have a look towards the future of the technology, that how it is going to shape. And this is one of the possibilities of quantum machine learning, because the field of even coding or programming, it is changing. The machines, they are self-developing, self-growing, self-learning paradigms, they are happening. And then the drug discovery, it's a very big field where we are, a lot of work. So understanding of DNA, genetics and other fields, they are heavily using the field of quantum there. So we need to, we can discuss about what strategies can be thought of where we can encourage the students, underrepresented students, to work, to go with this emerging and exciting field of quantum technology. So thank you so much. This is what I wanted to share with you all.
Firstly, this is a very interesting and comprehensive, exhaustive presentation on what we should be doing. But I'd like to share, because we are a somewhat more exclusive group and further seeing group. I will advise all of you to read, if you have not seen earlier, a very interesting article which is also made into a video with the title, The Usefulness of Useless Knowledge. This is written by Alex Flexner, who was the founding director of Institute of Advanced Study, Princeton, which we know has been the leading. And because a whole lot of people want to know what will you do with it. Even for example, school mein ye kyun padha rahe ho, ye wo. So Alex Flexner is a very nice, and you don't have to buy the book, you just look for it in YouTube video, 1 hour lecture on the usefulness of useful knowledge. Usefulness of useless knowledge. The other point I want to emphasize, because we get carried away with the technology and even more than that with the marketing and so on, we forget another very important aspect. That aspect is mathematics. When we see our DST person struggling is because he's looking at phenomena, he's not understanding. And there is a very interesting fact of life which everybody is worried about. How is this world so much a reflection of mathematics? Because when you do things in mathematics, you have nothing to do with the world. Now with Professor Suresh Chandra, you talk about numbers, and you suddenly talk about numbers which are square root of negative numbers. The pure abstract concept. Square root of -1 and this thing, complete abstract. Nobody could imagine what it means. Suppose I ask you to explain what is the meaning of square root of -1. But can you do electrical engineering without complex numbers? You can't do quantum also without complex numbers. These are when we are describing the state function of any quantum system, complex number is an integral part of it. And the reason why people are not able to explain superposition, because superposition is a mathematical concept. Now you are saying, mathematically it is very simple. You take vector space, you take two vectors, you take the sum of those two vectors, that's another vector which is therefore in that space and in another quantum state. Now when you try to say, yeah, electron going up, down, then you can't do it ever so often. And what is very interesting is that, take a thing like Fibonacci sequence. You heard Fibonacci sequence? Oh, the flowers, petals are in Fibonacci sequence. Various other things are in Fibonacci sequence. So in fact, this has got some people to say, is God a mathematician that is basically doing everything? And what I want you to appreciate is that quantum mechanics and quantum technologies is the next state of mathematics application to our real life. So that is the important thing. And so just like we took simple thing was integers, numbers, fractions, decimals, this, that, vector. So this is what it is. It is also very important. He talked about a portion which is developing very fast, called topological quantum computing. And Bill Gates has put a lot of money in this, and Microsoft. He showed all this donut kind of a thing. The idea is we are saying qubits decohere very easily. But if we can tighten these qubits in some form, in what is mathematically called a braid in topology, he talked about a donut in topology, but a braid in topology, and braid in simple Hindi is chutila. चोटी बांध लो तो नहीं खुलती आसानी से, खुले बाल रखो तो फैल जाते हैं. So they are saying rest of the world is doing खुला क्यूबिट, फैल जाएगा, मैं चोटी बांध दूंगा. चोटी बांधने के लिए मुझे टोपोलॉजी चाहिए और ब्रेड्स. उसके लिए बिल गेट्स हैज फॉर लास्ट सेवरल ईयर्स हायर्ड अ फील्ड मेडलिस्ट इन मैथमेटिक्स, फ्रीडमैन. उसको रखा, उसका काम है बस तुम सोचो मैथमेटिकली ये कैसे करेंगे. एंड ब्रेडेड क्यूबिट्स is going to be the thing which will allow this to be stable for a little more time. He's mentioned D-Wave several times. I once saw a video of the CEO of D-Wave, and people were asking him a very interesting question. They said, with this kind of a thing, what should our school leaving students be ready for the future? And he said very bluntly, while they are in school, they should learn all the mathematics that is being taught in college. And there is no reason. See, if I can teach you solving simultaneous equations with 2 variables, with 3 variables, why can't I say with n variables as well? And you don't have to do the calculation, the computer will do the calculation. But conceptually, there is no reason why matrices, vector algebra, etc. is not, and that applies both for AI and for computing. So, in fact, my post today has been very interesting. I posted something on LinkedIn, Twitter, etc. I said, if a young person comes to me for advice as to what they should be learning to be future ready, I say skill of self-learning, using AI to be a better learner, and using this to learn English, which is the language of international communication, mathematics, which is the language of nature. This was said by Galileo 1600. Quantum, which is the nature of nature, and AI, which is what is going to build you into innovation and automation. So this is a very important point. And what I'm trying to say is, and I'm very serious about it, we use the phrase quantum jump. We are going to have a situation where you will have a set of people who just will not fit into the future society because they cannot comprehend what is happening. We already saw that in that head of DST person. He has no idea what's going on. And this is what is going to happen. So we have to create mechanisms, and that's why I showed that other video, that from a child to a school to everybody has to be oriented towards appreciating these kind of things and becoming curious, interested, lifelong learner. Sensors. He talked about sensors. I want to share this. So when I was doing my PhD, I am very delighted these days because exactly what I've been doing 60 years ago. And at that time it was considered faltu ka kaam and so on and so forth. And I remember people asked, what has this got to do with, and I coined the phrase TC Mitts, the celebrated man in the street. I can't say Aam Aadmi because that is political today. So man in the street, how does he benefit from all this? But today, I say this, now we have an answer. The man in the street is on the right street because of this. The GPS uses atomic clocks, which is what we are going to talk about. And what mathematics does it use? Not Euclidean geometry. It uses theory of general relativity. Theory of general relativity says space-time curves according to the mass moves according to space-time. Using general theory of relativity and atomic clocks as quantum sensors, we are able to put the man on the right street. Same thing for medicine. I just had my MRI yesterday. MRI was also something which the physicists did. They did that. Rabi found nuclear magnetic resonance and this and that. But what they have to put you into a big tube, huge magnetic field, 300 Tesla, put it there, lots of sound, lots of this, etc. With quantum sensors, it will become like maybe a torch or a helmet or something they will put and everything will be able to see. Let me spend a minute on that also. See, the whole game of sensing, and he showed all these things away, is mathematically solving the inverse problem. We solve the direct problem. Given these three masses, what will be the gravitational field? Given these three charges, what will be the electric field? Given this, what will be? Now we are saying, we have measured the field. Can you say what is the distribution of mass? Can you say what is the distribution of charge? And so on. And big companies today, big companies like BHP Billiton, Rio Tinto, all these mining companies are doing exactly that. They are measuring the gravitational field and trying to see whether there is oil, there is mineral, what kind of thing is there, and so on. And it is physicists who are doing this inverse problem. Again, fortunate in my time, I have done some of these, also published papers in this. But what we would do, we would assume that it is a spherical radial distribution so that I can say the answer is a Bessel function and my result is going to be a series of Bessel functions and so on. But today, now with quantum sensors, very weak measurement of this thing, you will be able to do this again with the help of quantum computers. So you need both of these. There's a very big joke about physicists, and since I have a fellow physicist, he must have seen. There's a book up, you can look, there's a very nice book. The story goes that a lot of people who were farmers, agriculture, etc., had cattle, etc., had some problem. So they went to the best physicists. Physicists are considered brilliant. They went to the best physicists and they worked on it, and after a few times produced some report. The title of the report was, Imagine a Spherical Cow. So they said, if the cow is spherical, then I can solve everything. But then they said, but this is very difficult. So we said, okay, then imagine a cylindrical cow. so physicists can only do some model. The spherical cow, cylindrical cow, they can solve. But for real life, you need quantum sensors, quantum computers, quantum calculations, and so on. So I hope you enjoyed this part, and now we'll request.
मेरी अब एज ए सिटीज़न परेशानी हिंदुस्तानी सिटीज़न या अंडरवर्ल्ड की है। मैं फ्रॉम माई PhDs इन डेज इन 70s, एक साइंस या एक नया कॉन्सेप्ट आता है, हम लोग उस कॉन्सेप्ट पे जुट जाते हैं और कंट्रीब्यूट भी करते हैं। बाय द टाइम वी हैव फुल्ली मास्टर्ड दैट, एक नया कॉन्सेप्ट आ जाता है, हम उसमें कूद जाते हैं। तो हम लोगों की जो कंट्रीब्यूशन है उससे बहुत कम रह जाती है, क्योंकि हम एक लर्निंग पाथ पे रहते हैं हमेशा। एक अमेरिका में कोई नई चीज़ आई, हमने उस पर शुरू कर दिया काम, फिर नई चीज़ आई तो मतलब रिसर्चर्स की बात कर रहा हूँ या यूनिवर्सिटी, वो फिर दूसरा काम शुरू कर देते हैं हम लोग। तो हम लोग जो है कंट्रीब्यूट नहीं कर पाते हैं इससे उस पर, क्योंकि आपका काफ़ी वाइड एक्सपीरियंस है, मैं इसीलिए चाहता था आपका।
This entire quantum thing is due to a person called Max Planck. जब मैक्स प्लैंक फिजिक्स करने चला तो उसके प्रोफेसर ने, जर्मनी में उसके प्रोफेसर ने, ही सेड फिजिक्स में कुछ करने को है ही नहीं, एवरीथिंग हैज बीन डन, देयर इज नथिंग टू डू इन फिजिक्स। बट व्हाई आई लाइक दिस स्टेटमेंट, मैक्स प्लैंक सेड आई डोंट केयर, आई वांट टू अंडरस्टैंड इट। एंड दिस इज व्हाट आई ट्राई टू टेल पीपल, दिस जो व्हाट ही इज सेइंग इज दिस रेस की लेटेस्ट क्या है उसको नहीं, spend your time trying to understand it. Max Planck was trying to understand what his professor said, there's nothing new to do. He said, I don't care whether I do nothing new or not. I want to understand what is it. And in trying to understand, he figured out that. And his context, when I was in Canada, very active scientist, one person wrote the article on this. He said, we only have institutes for advanced study, advanced physics. We should have centers for backward physics, where the old physics we really understand. I really like that fellow. That's why I appreciate. He said, every time we are chasing to the new topic. Instance. हाँ. हाँ. हाँ नहीं करेक्ट, इसीलिए नहीं, इसीलिए मैं कह रहा हूँ। सो हम करेक्ट, सो देयरफॉर दैट्स एग्जैक्टली, सो नाउ व्हाट वी वांट इज, एटलीस्ट आई एम, नहीं, आंसर इज टू स्प्रेड दिस आउट सो दैट पीपल आर ड्रिवन इंट्रिंसिकली, नॉट एक्सट्रिंसिकली। मेरे इनफैक्ट बहुत अच्छे वो थे, इलाहाबाद के प्रोफेसर थे, उनका था कि गवर्नमेंट टाइम टू टाइम थ्रस्ट एरिया कहती है, और वो एक्टिव साइंटिस्ट से कहते हैं दैट इज एरिया थ्रस्ट ऑन अस। So, but if you allow, see, eventually all science goes by natural curiosity. हाँ नहीं, पर बट व्हाट आई एम सेइंग इज दिस ऑन MRI, यही जो नील डिग्रास टाइसन दिखाया था इन्होंने, उसका बहुत अच्छा है। उसका कहता है कि मेरा प्रोफेसर एस्ट्रोफिजिक्स में इंटरेस्टेड था, वो समझना चाहता था एलिमेंट क्या है, उसने निकाला कि मैग्नेटिक रेजोनेंस से पता चल जाएगा। एक डॉक्टर ने पकड़ लिया, कहती है ऐसा हो सकता है तो मैं टिश्यू के अंदर देख सकता हूँ, तो कहता है दिस वाज क्रिएटेड बाय ए फिजिसिस्ट हु हैड नो इंटरेस्ट इन मेडिसिन, नो आइडिया ऑफ डॉक्टर, बट क्रिएटेड इट। सो द आइडिया इज that we should not worry too much, दोनों हैं, एप्लीकेशन ओरिएंटेड भी करें, but mostly try to understand better, and that's why I like that Max Planck story कि ठीक है नया नहीं होगा ना मुझसे, मैं समझने की कोशिश करूँगा. हाँ नहीं पल्स से सब पता है. ये ज्योतिषी वाला है नहीं, इज इट द पल्स और द ज्योतिषी? हाँ चलिए फिर वो बाद में बात करेंगे, अभी जाना इनका आगे बढ़ जाता है. नहीं ये सारा olfaction is a quantum phenomenon. There is no, that's why we'll take it further.
Have you revised your PPT or which is same thing? Otherwise मैंने उसमें कॉपी कर रखा है. हो जाएगा. ये भी लगा. उसमें कोई ऑडियो है?
Dynamic nature is quantum. Dynamic nature is quantum. You have to make a quantum computer if you want to. Nature is quantum और इसके मैंने dynamic लगा.
अच्छा वो तो आपकी लैपटॉप का है.
पहले इसमें पंच तत्व में मान लिया.
बैठना चाहिए.
फिर हम periodic table तक छोटा सा. फिर हम ये प्रोटॉन न्यूट्रॉन ग्राफ और इसमें पहुंच गए. आज की तारीख में जो लास्ट में चल रहा था थ्योरी की तरफ जा रहा था. 2 मिनट स्ट्रिंग थ्योरी
वो बोलना चाहते हैं.
अच्छा
उनके बाद शुभ्रांश का ज़्यादा लंबा नहीं है.
some phenomena which is not explained by products. ये चलता रहता है.
इसमें सर एक और चीज़ है, आपको याद होगा, वो जैसे गार्टनर हाइप साइकिल है. तो सुरेश जी जो कह रहे थे कि हम लोग हमेशा उसी में लगे रहते हैं और फिर नई चीज़ आ जाती है. सो द इनोवेटर्स एंड देन द अर्ली अडॉप्टर्स, लेट अडॉप्टर्स एंड लेगार्ड्स. लेगार्ड्स वाले सबसे बाद में होते हैं. सो दिस इज
इससे चेंज हो गया, इससे आगे.
एक है जो लोग कर रहे हैं, तो जो लोग सुपर कंडक्टिविटी में काम कर रहे थे वो अभी भी कर रहे हैं. जो हाई टीसी ढूंढने में लगे हैं वो अभी भी कर रहे हैं. सी मीडिया अटेंशन क्या आती है, मतलब मैं क्यों आजकल बड़ा खुश हूँ क्योंकि मैं तो ये पीएचडी कर रहा था. मेरी पीएचडी हाई कंडेंस मैटर फिजिक्स में. ये जो बातें हो रही हैं वो हमारा काम ही ये था तो फंडामेंटली से कॉपर की क्या प्रॉपर्टीज़ होंगी, सिल्वर की क्या प्रॉपर्टीज होंगी फ्रॉम इट्स एटॉमिक स्ट्रक्चर. फिर क्रिस्टलाइन स्ट्रक्चर है, फेस सेंटर्ड सॉलिड, बॉडी सेंटर्ड सॉलिड, ये स्ट्रक्चर. फिर अगर इसको हम एलॉय कर देते हैं तो कैसे होगा. मेरी सारी पीएचडी थीसिस का टाइटल ही है स्ट्रक्चर ऑफ ऑर्डर्ड एंड डिसऑर्डर्ड सिस्टम्स. सो पॉइंट क्या होता है, बीच में आप और चीज़ करने लगते हैं और करते रहना चाहिए. दोनों तरह के लोग होते हैं. एक होते हैं जो एक फाबर था, वो ज़िंदगी भर सिर्फ चींटियों का मूवमेंट देखता रहा. तो तरह तरह के वो लोग होते हैं और उसमें कोई एक राइट रॉन्ग नहीं है. द पॉइंट इज दैट एंड ह्यूमंस by nature are curious to understand. And some people, Einstein ने बड़े famously कहा, उसने कहा कि मैं कोई आपसे ज़्यादा फर्क नहीं हूँ, only I stay with the problem longer than you do. हम लोगों के यहाँ डिपेंड करता है, प्रोफेसर तो कहना पड़ेगा, एक है सब रब्ती माया है, क्यों परेशान हो, सब रब्ती माया है, एक नहीं हम समझना चाहते हैं, एक है क्या, जैसे मैं आजकल आपको बताऊँ बड़ा इंटरेस्टिंग है, so I am at whatever age and stage, but I'm very excited because I'm trying to learn now the physics of living systems. अभी तक तुमने फिजिक्स ऑफ डेड सिस्टम्स पढ़ी, इलेक्ट्रॉन, प्रोटॉन, न्यूट्रॉन, आज मैं बायोलॉजिकल सेल की देख रहा हूँ, ऑटो इम्यून डिसऑर्डर क्यों होता है, मैं पब्लिक में नहीं कह सकता हूँ, और मेरा अंडरस्टैंडिंग है कि ऑटो इम्यून डिसऑर्डर इसलिए होता है कि क्वांटम टनलिंग की वजह से जो उसको दोस्त लग रहा था वो अब एनिमी लगने लगा है। ऑटो इम्यून डिसऑर्डर यही होता है कि जिसको कल तक इम्यून सिस्टम तो ठीक चल रहा है, वो उसको दुश्मन समझ के अटैक करता था, अब वो आप ही के सेल को दुश्मन समझ के अटैक करने लगा है। And somewhere inside I believe it is quantum tunneling which is happening. I need to find out what is the potential which it is being able to do. क्योंकि अपने आप से तो नहीं होगा ना, होगा तो किसी न किसी phenomenon से. So anyway, क्योंकि इन चीज़ों में लगा हो तो मेरा तो काम अच्छा चल रहा है जब तक.
So friends, let's welcome Subraj. I request him to introduce himself to tell about his work. And then he wants to make a brief presentation on quantum biology.
इसकी ज़रूरत नहीं है ना इसकी? Okay. Hi everyone.
इसमें आपने इन्होंने कहा ना बड़ा अच्छा कि he will introduce himself. तो एक बड़ा famous quotation है. The physicist is an atom's way of understanding itself.
Yeah. Hi everyone, I know we don't have a lot of time left. My presentation is going to be pretty short. A lot of the points have already been discussed by Ramesh sir and MM Pansar as well. Before I begin, I'd like to preface it by saying I'm not an expert in anything. I'm pretty young. I turned 20 last month, so I'm very young to all of this, and I'm self-learning. As I've mentioned before, I'm not doing any traditional college. I have my own startups, but I'm self-learning a lot about physics and biology, and I'm just trying to mash up different subjects to see what I can come up with here and there. Also I'm not an expert, I'm just saying that again and again because I don't know if you find inaccuracies in what I'm saying, please do correct me because that would be really appreciated. My name is Shubhransh Rai. When I was 17, I started my own animation studio. And now today I stepped down from this position of CEO because it was taking a lot of time, but I'm still retaining the position of founder and the founder and CFO of Studio Eclipse. And I'm also the creator of Verve Visual Agency. We basically deal with media generation and all of that. Firstly, before we begin, I'm going to discuss a bit about quantum mechanics, which already has been discussed by Ramesh sir. It's the fundamental theory of physics that it provides the framework of understanding matter and energy on the most fundamental level, right? Atoms and subatomic particles. We've also obviously discussed most of what has been discussed in here, so we're not going to spend more time on quantum mechanics. Obviously, a lot of, so quantum entanglement has also been discussed. I'm just going to give another one of my own viewpoints. Something which Neil deGrasse Tyson's podcast, I think, did not mention, or maybe it has been mentioned, but I just did not catch it, is that quantum entanglement doesn't really care about the distance. It can also happen within the span of light years. It doesn't matter. Obviously, the decoherence constant can be a problematic factor. But for example, if two quantum particles are entangled, let's say two electrons are entangled, whether you keep them light years apart, it's not going to make any difference. If the spins are correlated, if the spins are entangled, let's say the spin of atom A is positive and the spin of electron is negative. So the moment you observe the spin of electron A, if it's positive and it's correlated to the other electron which is negative, the immediate response would be, even if the electron is light years away, it still would be a negative spin. That's the main basic idea of quantum entanglement. Moving on with this topic, introduction to quantum biology. So it's a new field it's like a melting pot of physics and biology, right? And it's an emerging field that holds promise for transformative advances in both quantum physics and life sciences. We can use it for a lot of things, such as like a deeper understanding of how biological systems work, and it can lead to major medical breakthroughs as well. So now I'm going to discuss a bit about quantum sensing, as Ramesh sir has already talked about. So superposition is like, obviously we've discussed about superpositions. Particles like electrons and atoms can exist in a superposition of multiple states. So this property is used in quantum sensors to create delicate quantum states that are sensitive to external influences. So in context of something like biological sensing, quantum sensors can exploit superposition to create quantum coherent states that can interact with target molecules or biological systems. So this is just one of the quantum sensing technologies that we can produce in the later. We can also use entanglement, and for biological sensing as well, entanglement can be used to utilize highly sensitive detectors that can react to even the tiniest of the changes in the biological environment. For quantum interference, we can exploit quantum sensors to amplify small changes in the environment. And quantum interference can amplify the effects of molecular interactions, allowing for even the minute changes to be detected. The other is spin-based sensing. So quantum sensors can also detect changes in the spin properties caused by interaction with the biological molecules, providing information to the system state. The next one would be precision measurement. These are just some of the ways in which you can use quantum biotechnology to actually come up with a lot of medical innovations and biological innovations as well. So by using quantum principles as well, the charges that quantum sensors can measure quantities like magnetic fields, electric fields, temperature, and time with exceptional precision. So in context of biology, changes in these quantities can be indicative of molecular interactions, cellular activities, or even disease states. The next one, the last one in general, would be quantum metrology, and it's the science of making precise measurements using quantum principles, right? So quantum sensors leverage quantum metrology techniques to surpass the limitations of classical sensors. This allows them to detect and characterize biological changes that might be beyond the reach of conventional technologies. The next, obviously, Ramesh sir has already discussed this as well. Quantum computing is just a cutting edge paradigm computing that leverages principles of quantum mechanics to perform complex calculations here and there. Ramesh M. Pansar has also given us the task of giving a simpler answer to why quantum computers can do the tasks which are much more at a faster pace than classical computers, which I am going to give you an answer to, sir, in 1 month. As good as I can, at least. So at the heart of quantum computing's power for simulating molecular interactions are its unique position. So quantum superposition enables different molecular configurations and interactions in parallel, which dramatically simulations is the first thing that can be used for quantum superposition. The next is quantum entanglement. Again, you already know what entanglement is. So this property can be used to exploit a model complex interaction between atoms and molecules more effectively, and as entanglement allows quantum computers to represent highly interconnected systems with much greater efficiency. And quantum parallelism is basically quantum algorithms can leverage superposition and entanglement to perform calculations on possible solutions simultaneously at a much faster rate. Like a multiple amount of calculations can be done at the same time. So for molecular simulations, that means that quantum computers can explore a vast space of possible configurations much more effectively than classical computers once again. And the last is quantum annealing. So it's like they are specialized quantum computing devices designed to optimize complex systems and help find the lowest energy state of molecules, which is crucial for understanding stability and reactivity. This has, I'm going to go over this. This has the potential for a lot of things such as accelerated drug discovery, materials design. We obviously know quantum computing has been used for protein designing and a lot of other stuff. which can be really beneficial in the medical field. It's absolutely innovative, and I'm genuinely so optimistic about a lot of people. So when people question me about stuff, and for example, even in that video, they were like, in 5 years, can I have this quantum computer in my basement? Obviously, I'm not that much of an optimist, but I do think in a decade and a half, the way we're going to see life and the way we're going to see civilization itself has the potential to completely change. Like, I think a lot of people are going to be left behind because the very idea of how to live is going to completely alter like everything, every perception that we have currently. And I do think a lot of people are ready for that change, and I don't think a lot of people are ready for that change at the same time. Reaction mechanisms and catalysts, it can help elucidate intricate details and chemical reactions with catalytic processes. It can provide insights into reaction mechanisms, and which were previously very difficult to understand actually. It's still in the early stages of, due to like technical challenges, right, obviously, and stabilizing quantum systems is extremely hard. Researchers are still making extremely steady progress, and as this technology ends up maturing, it has the potential to revolutionize our understanding of molecular interactions, enabling breakthroughs in fields that heavily rely upon complex simulations. This is one of the most interesting part of quantum biology, would be genome sequencing. So genome sequencing is the process of determining complete DNA sequence of an individual or an organism's genome, which comprises of all the genetic material. It involves deciphering the precise order of the nucleotide bases. So these are some of the nucleotide bases that you can obviously come up, you obviously know, they make up the genetic code of any sort of an individual, whether it be humans or any organism. The other techniques that we have for this are optimized sequence alliance. So for genome sequencing, we can align DNA fragments from a specific genome reference, and this can require a lot of computation, right? But with quantum, especially for larger genomes, for like a genome of a human being, let's just say, these are very large genomes, and quantum computers, with their ability to process multiple possibilities simultaneously at the same time, could significantly accelerate our sequence alignment by exploring multiple alignment scenarios at once. The next is de novo assembly, which is very, very interesting actually. So de novo assembly involves reconstructing genome sequences from short fragments or without any reference genome. They don't require any sort of a reference for this, and this process is actually so computationally intensive that no type of a classical computer can ever handle this. And they can obviously benefit a lot from quantum computers' ability to analyze complex combinational patterns. I did a spelling mistake over there. Complex combinational patterns and optimize assembly algorithms. So obviously the results can be absolutely fascinating from the way we can go about this. Variant calling is not that important for this, at least not right now. The next would be structural variant detection. So detecting larger structural variations in the genome, such as duplications, inversions, translocations, these are some of the variations. It's very crucial for understanding genetic diseases, right? Quantum computers could handle complex computational challenges associated with structural variants much more effectively than classical computers again. I'm not going to talk about all of them. Let's skip to the sixth one, which is population genomics. So analyzing the genetic diversity within population is very essential for understanding evolutionary processes and identifying the risk factors as well. So quantum computers can help accelerate large-scale population genomic studies by processing and comparing genetic data much more efficiently. Let's just say we found the DNA remains of an organism that has gone extinct for 100 million years, let's just say. I'm just putting a number out there, don't quote me on this. We can essentially use that DNA to run so many simulations again and again and again that obviously I'm not going to say we can replicate the organism again, but we can understand so much more about the organism than we previously did. For example, even right now, a lot of people are saying dinosaurs were nothing the way we actually thought of them. There's a lot of possibility that they actually had fur, and they did not roar, but more like they mimicked sounds of a chicken. So that's how much of a low understanding we have genetic diversity at the very least. The next is that the PPT is about to be over, just letting you know. So the next is quantum nanotechnology and drug delivery. So quantum dots and particles represent innovative approaches in the field of targeted drug delivery. So think of it this way. Quantum particles are very own created these artificial sort of robots. They are obviously going to carry drugs to the specific parts of your body. That's maybe not just science fiction anymore. Maybe that can be used in one way or the other. Quantum dots, I'm just going to explain what they are. Due to their size, quantum dots are basically nanoscale semiconductors which are unique optical and electronic properties. They have unique optical and electronic properties. They have obviously quantum dots, due to their size, their fluorescent properties, can serve as imaging agents for tracking the drug delivery processes in real time. So this has a lot of uses in the real world, no matter how you look at it. You can take a picture of this, and if you want, I can send the entire PPT on the group as well, so you can read it over there. And so one more thing, ethical and regulatory considerations that we really need to think about is that when we get into this world of genetic manipulation through using quantum computers, we need to look at a lot of stuff such as ethical concerns from medical fronts. Data privacy is a thing. Any sort of let's say a company which has an access to a very strong quantum computer which can perform a lot of genetic mutations would obviously have a lot of genetic data of not only individuals that are born right now, individuals that have been on this world for the longest time possible. They would have a lot of genetic data, and is it okay for us to trust those extraordinarily huge companies with such genetic data? That's one thing that we really need to focus upon. And there's a lot of other things such as equitable access to quantum technology, because everyone needs to have an overall access to this, to not lead into even greater disparity that we currently already have. Future prospects is just open for the floor. You guys can also participate in this. There's a lot of future prospects that we can think about with and the thing is, when we introduce something like quantum computing to anything, biology, chemistry, just about any subject, you can think about in a way that subject is going to just exponentially explode, I guess, because there's so many new things that are going to be introduced in that subject that we can't even begin to fathom or begin to comprehend. There's a lot of, obviously, despite these extraordinary achievements that we currently talk about, despite these big talks that we constantly think about, there's challenges such as error connections in quantum systems, algorithm refinement, and a lot of ethical concerns as well, and around the data privacy and all of that stuff. Collaborative efforts among quantum physicists, biotechnologists, medical researchers are imperative to harness the full potential of quantum biotechnology, paving the way for transformative breakthroughs in healthcare and biological understanding as well. So it's very important for us to run fast, but check how we're running as well. We don't want to slip on our own shoes. This is just a quick summary of it. We discussed quantum mechanics. I was about to discuss the double slit experiment, but I took it out when I was editing, because my PPT was way too long for this. We discussed quantum entanglement, quantum computing, quantum biotechnology, targeted drug delivery, ethical concerns, and the ongoing research as it holds promise in drug discovery, genomics, imaging, and a lot of other stuff. This is me. My name is Shubhransh, again, Shubhransh Rai. For contact information, that's my number and that's my email. I'm really thankful for all of you. Thank you.
Mr. Gino is here with us, and I think he has to leave because he wants to talk to us for a few minutes.
Good afternoon, everyone. I'm just arrived 4 weeks ago in India. It's my first visit, and I'm here just as a tourist. But Geology asked me, if I come to India, then you have to give something back. and that was the assignment. As you want to do there's something about AI, and I'm a special educator. I work with autistic students from the age 12 to the age 19, and we prepare them for the next level. It used to be, or could be university or one level below. So I'm an educator, special educator. I also teach physics. So lovely presentation. I like the way you talk to us. You make us listen that very well. So great talk you did with me. So that was the assignment. Come to India, do something with AI and autism. And I designed a product because I believe that if you have an autistic son, daughter, student, it's hard for us as teachers, as parents, to communicate with them. And I'm here in India to find out if AI is a possible solution to have a communication with your child. And that is my research. And I will research at schools. I will go to the different corners of India to find out if my approach, how I work in the Netherlands, could be replaced by AI with the same methodology throughout India. So I can leave the device here, and it could be used in the Indian society as well, because we in the Netherlands are a little bit further to address special children, how to deal with them. And I want to share that knowledge in a device so that can be used here in India as well. I got it even in my bag, but I can show it, but I already showed it to Sir just a moment ago. It's a little box, just this one. And it contains a speaker, a microphone, and a lovely button that changes from color. So we put it here. And then what it should do is that it enhances communication between you as a parent, teacher, caretaker with a student or child with autism. And this is just a third person in the room that you can ask something to, and it replies, so that you can talk about the answer or suggestion that has been given. And because it speaks very slow, that is one thing you must learn from me today. If you have an autistic son, speak slowly with clear words, perfect words. He speaks or she speaks perfect English or Hindi, Bengali, you name it. It's the right pitch that it is pronounced. So that's what it does, and without emotion. Because if you have autistic brain, your brain functions differently. Everything that's coming into your brain, it has to be processed. So if you reduce the lot of information coming to you, they understand the message delivered. So that is what this box does, and that's what I try to do in India, to do some case study. In the end of 3 months, I will deliver the results to Dology, and maybe we can turn it into a device for the Indian market, so it can be helpful, not to the rich, because they already have a lot of money to gain therapy, coaches, etc., but for the common Indian who don't have that resources, they can buy that for a low price, and they have someone they can talk to and gain answers from that. So that is the noble, I think, that we're trying to do. And I just want to share that story with you all today. And maybe if you say, hi, maybe I have a school, or maybe I want to hear more, talk to Dology, and we would like to participate or collaborate with more people to make it a value project for the markets in India, and that is my main focus. And I'm a teacher, so I love to share knowledge. I also do quantum computing at my school. I want to raise that awareness as well, so maybe we can collaborate on that as well, because I believe if you can deliver the message just about quantum computing itself, it switches in our minds, so it can be the future where we're heading to. It's just in the different area yet. Yeah. So thanks for the time. Yeah, I will leave mine. Thank you. Oh, and my name is Zeno. That's what I'll talk to you about. And I left this lovely Indian name because I'm from Indian background, and my second name is Umesh. So that's what I'm sharing today.
Okay, so Pant sir for the final remarks.
So we've had a very interesting session. I don't know how much. ये last वाला PPT लगा सकते हैं? चलो. So what I've done is that, as I said, I want to have it as a bigger mission. Many of you are aware that India is the only country which in its constitution directive principle has a statement, Article 51AH, that it is a duty of every citizen to have a scientific temper. Now, the idea of a scientific temper was talked about by Jawaharlal Nehru long before independence. He wrote about it in Discovery of India and so on. But after independence, he was quiet on this. He would go to Science Congress, he would go to NPL, but he did not publicly talk about scientific awareness. And I was always wondering what happened to him. He wrote so much before independence. Then one day, like Buddha's enlightenment, it occurred to me, he saw that Gandhi ji was murdered. He said, उनको तो राम राम कहने वाले को तो इन्होंने गोली मार दी, मेरी तो बोटी बोटी काट के मिन्स मीट बना देंगे. So he stopped talking science. And then we had a model where science meant only for engineering. Even science for science was not. I did a session once with class 12 teachers of Kendriya Vidyalaya. They are all very bright. I asked them, when a student comes to your class and you teach physics, does he think of physics or does he think only of engineering entrance exam? He said only engineering entrance exam. So the problem that has happened is we have created it. What I want to do is quietly and not without much publicity because there will be hostility, just let this information go around. So very honestly, इसको लोग viral method कहते हैं, पर मैं उसको cancer method कहता हूँ. आप अपनी बात ऐसे फैलाइए कि लोगों को पहले पता न चले, जब पता चले तो बहुत देर हो गई है. So I call this the cancer method of engaging. तो वो, and I have therefore created, and यहाँ detail नहीं बताएंगे, but मैंने actually क्या करा है कि एक जैसे ये तो एक करने से एक 1 week long program बनाया है about quantum awareness, 5-day week का, और एक 1 month long बनाया है with a little more. उसके बाद फिर अब आप मार्केट में जाइए, जो आपको समझ में आता है वो करिए, करने कराने का वो. और मेरा पढ़ाने का उतना इरादा नहीं है जितना access to resources and self study. So quickly I will take you through these slides very quickly, and या आप करते चलिए, आप आई हैं जब यहाँ बैठ, हाँ दिखाते जाइए. तो मैं क्या कह रहा हूँ कि सीढ़ी चढ़ते जाना है. मैं शुरू की सीढ़ियों की तरफ ले जा रहा हूँ. पहला है a 1 week WhatsApp delivered program for curious adult. Anybody who's interested वो करें. और मेरा अपना conviction है that people will find their own things out of it. This idea that all of us will do it, we study physics, but all of us will become physicists is not important. So then I have a QIL, Key Quantum for Young Learners, 1 month program, best suited for children in class 11, 12 or first 2 years of university. Next. And I said, but quantum of what? सारे लोग quantum की बात करते हैं, पर ये आया कहाँ से? And I want to emphasize this, that when I was at that stage, I also could not articulate it well, but now I can articulate it better. So in the days of screen watching, TV, computer, etc., you understand that that image is made of pixels. And you know अगर resolution बहुत ज़्यादा कर देंगे तो pixelation हो जाएगा, image नहीं दिखेगी. This is what quantum is. When you look at the quantum level, you are seeing those pixels and not seeing the big image. If you see at a different level, you are seeing the 1 million pixels, it looks like one continuous image. This is what quantum is about. And so in a pixel, it is the area which is the thing. Here it is action. The term in physics, energy multiplied by time. So in any process, 0.6 into 10 to minus 34 will become a quantum thing. It is not only atoms, molecules, this, that, whatever. It is this which is like the pixel size. That is why it is. And the program is 1 week program में quantum in the news, the Indian National Quantum Mission, global quantum initiatives beyond the Indian National, because what I want to say, beyond the Indian National Quantum Mission is also more important. And finally, quantum readiness. Next. उसको थोड़ा detail, quantum in the news में quantum move from laboratory to breaking, Google's quantum supremacy, IBM's quantum roadmap, Microsoft road less travel, remaining updated on quantum. See, this is a very important thing I want to say. Earlier, when we were growing up, we had no idea what is going to happen. But today, I had that slide of stairs and so on. Each of these companies have given their quantum roadmap for every year and the money they are giving. So आपको पता है इसको 100 क्यूबिट का बनाना है, 500 क्यूबिट बनाना है, 1000 क्यूबिट बनाना है, 10 लाख इतना $1 बिलियन खर्च करेगा, तो यू हैव टू बी रेडी फॉर इट. पहले ये नहीं पता था कि क्या होएगा, कैसे होगा, कहाँ से होगा. Now at one level, most big companies, their next 5-year, 10-year plans have been publicly declared. ठीक है, they may fight each other. Google में से आए, chief quantum से IBM में से, no, that is not so good, I can also do this. But for a professional, there's opportunity everywhere. And that is what I want to emphasize. Next. Indian National Quantum Mission में शर्मा जी ने बहुत अच्छा समझा दिया, कंप्यूटिंग, कम्युनिकेशन, सेंसर्स एंड क्वांटम मटेरियल, ये वाली बात है. और इसमें ऑलरेडी आप लोगों ने सुना कि 2-3 years ago, graphene was very much talked about. Graphene is an example of one layer of carbon atoms, and it has properties which are amazing. And this is what quantum materials is all about, that you have brand new set of materials on that level. Next. Day 3, global initiatives. What is the UK doing? When you read UK, you say, oh, India वाला तो इसी का copy है. Then US is very interesting. हम सब लोग डोनाल्ड ट्रंप को बेवकूफ़ सा समझते हैं, but 2018 he signed that. He realized that US will slip behind if they don't do whatever. So now they will have courses on quantum engineering, 4-year programs on quantum engineering. So far only Australia has a program on quantum engineering. And then of course China though is, we don't even know, but it is on a trip of its own, but doing quite a lot. Then European Union ने एक बनाया quantum manifesto. They have also agreed that together we have to do something. Next. Day 4, I am talking about other topics. See, our problem is कि जो हमारे leaders हैं, they are limited in the traditional sense. Quantum qubit बनाएंगे 1000 qubit का. They've forgotten कि software चाहिए, application चाहिए, training चाहिए, ये चाहिए. So, impact of quantum on AI and genetics, quantum on agriculture, and raising a quantum ready workforce. This is the most important thing. और इसमें जो सबसे बड़ी चीज़ है, वो है mindset. You have to create a mindset. हमें कोई hesitation नहीं कहने में, I am part of the IIT system. IITs ने इतना लोगों की बुद्धि भ्रष्ट कर दी है कि they are not willing to see कि उसके अलावा भी कुछ हो सकता है दुनिया में. माँ बाप बच्चे सब IIT में करने को, उसके लिए कोटा भी जाएंगे, सुसाइड भी करेंगे. अच्छा, IIT में नहीं आके भी सुसाइड करते हैं, IIT में जाके भी सुसाइड करते हैं. समझ में नहीं आता. See, you would have thought IIT में जो नहीं आया वो सुसाइड कर रहा है, जो IIT में आ गया वो भी सुसाइड कर रहा है. So we have to actually encourage people to say there's a lot of things to do in the world which are encouraging. हो सकता है. और फिर फाइनली जो मैं कहना चाहता हूँ, इन्वेस्टमेंट इन क्वांटम. सबसे आराम काम क्वांटम का ये है कि आप कुछ खुद मत करो, क्वांटम की कंपनी में इन्वेस्ट करो. मतलब भाई, अगर इफ यू आर अ गुड इन्वेस्टर, यू हैव अ सेंस, तो देखो कौन सी कंपनीज हैं, कैसा कर रही हैं. जैसे कई लोग कहते हैं एप्पल फ़ोन खरीदने से ज़्यादा वो सुखी है जिसने एप्पल के शेयर खरीदे हैं. तो आई सीरियसली, इनफैक्ट मेरा अपना उसमें टेस्ट नहीं है, बट आई सीरियसली वांट टू क्रिएट अ प्रोग्राम ऑफ पीपल इन स्कूल लेवल हुज एम्बिशन इज टू बी, आई विल बी इन्वेस्टर. भाई वॉरेन बफे रोल मॉडल क्यों नहीं हो सकता? एल्बर्ट आइंस्टाइन ही क्यों रोल मॉडल हो? न्यूटन ही क्यों रोल मॉडल हो? एडिसन ही क्यों रोल? तो और एक बार बड़ा इंटरेस्टिंग हुआ, एक टीचर का मेरे पास मेल आया कि मेरी बेटी 12वीं में है और वो स्टॉक मार्केट में कुछ करना चाहती, मुझे लगा आप ही से बात कर सकते हो और किसी से बात नहीं। बट सी, stock market is a problem if you become a gambler. But if you are a researcher, engineer, you become an investor. So मैं वो भी करवाना चाहता हूँ कि कोई मिल जाएगा अच्छा आदमी तो क्वांटम इन्वेस्टिंग बताया करूँगा। नेक्स्ट, तो ये 1 month है, तो पहले 1 हफ्ते का सबके लिए, तो कम है 1 month is a little deeper. So 20 sessions. नेक्स्ट फटाफट चलते हैं। ये वीक 1 में ये होगा, नेक्स्ट वीक 2 में ये, नेक्स्ट वीक 3 में ये, नेक्स्ट वीक 4 में ये, नेक्स्ट। अब हर उसका वाई लर्न क्वांटम, फर्स्ट फॉर द सेम रीजन दैट एवरीवन शुड लर्न समथिंग अबाउट आर्ट, म्यूजिक, फिलॉसफी, बिकॉज इट शोज द वेरी बेस्ट अबाउट। पहले तो ये समझ में आना चाहिए। नेक्स्ट ये, अब इसमें बड़ी इंटरेस्टिंग है, यहाँ की ट्रेजेडी देखिए कि सत्येन बोस has done this। आधे पार्टिकल्स बोसॉन्स कहलाते हैं, बोस आइंस्टाइन पे होता है, हिग्स बोसॉन पे होता है, इसको कोई इज्जत नहीं है। इंडिया में भी उसको भारत रत्न नहीं मिलता, वो CNR राव को मिलता है, हम सब लोग जानते हैं। कहाँ CNR राव, कहाँ सत्येन बोस, वी नो दैट पर्सनली, राइट, उसको मिला है। तो इससे मेरा थोड़ा सा जन्मपत्री पे विश्वास बढ़ने लगता है कि उसकी जन्मपत्री में ही कोई खोट था। नहीं, आप बताओ, नहीं वो अलग है, बट नहीं, बट भाई आप सोचो, और उसको एक और चीज बढ़ाओ, वो नहीं नहीं नहीं, बट नहीं, कोई बात नहीं, आगे बढ़ेंगे। बस हम एक और चीज हम कई बार कहना चाहते हैं साइड में, अब यहाँ तो हम कह ही लेते हैं अपने मन की बात। बोस को भी रिकग्निशन कब मिला? जब आइंस्टाइन का नाम उसके साथ जुड़ा। रामानुजम का रिकग्निशन कब हुआ? जब हार्डी का नाम उससे जुड़ा। हिंदुस्तानी ने हिंदुस्तानी साइंटिस्ट को कभी सपोर्ट नहीं किया। आगे बढ़े, क्वांटम टेक्नोलॉजीज इन डेली लाइफ। तो ये अच्छा, मैं इसमें एक और कहानी आपको सुना देना चाहता हूँ, बिकॉज माई फेवरेट। हम लोग क्वांटम के माने सोचते हैं कोई कठिन मशीन, ये वो, उसी में कोई, पर मैं ये कहना है क्वांटम हर जगह है। और सबसे इसका सिंपल एग्जांपल आप सब लोग देख लीजिएगा। Every house has a kitchen. In the kitchen you usually have a gas, LPG gas. When you switch on the gas, it burns with a blue flame. उसी किचन के नमक को लेकर उसमें थोड़ा छिड़क दीजिए, the flame turns yellow. It is a quantum effect. So to see a quantum effect कहीं दूर नहीं जाना है, right there. क्यों? क्योंकि ओरिजिनली हाइड्रोजन गैस बर्न कर रही थी, ब्लू लाइन आ रही थी, अब सोडियम आयनाइज हो गया, सोडियम के स्पेक्ट्रम में येलो लाइन आती है, 5890 एंगस्ट्रॉम्स, 5896 एंगस्ट्रॉम, you are showing. So you can show quantum right here at your home without any special equipment. So it is a way of understanding life. It is not something different. Next, economic impact is there. Next, ये तो ग्लोबल लैंडस्केप, मतलब मेरा कहना है हर सेशन में ये चीज़ डिटेल में बताई जाएगी। Next, 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 next. So this is the other one. Finally, you can learn. तो मेरा क्या है कि मैं इतना काम कर सकता हूँ, 1 हफ्ते का जनरल, व्हाट्सएप के बाहर में नहीं जाने वाला हूँ, एक ये एंड 20 सेशंस ये। इसके बाद यू शुड बी सफिशिएंटली एम्पावर्ड टू गो एंड डू फ्री कोर्सेज एंड इवन पेड कोर्सेज। मैं पेड कोर्सेज के खिलाफ नहीं हूँ। बहुत लोगों को ये होता है कि भाई जब ये चीज़ सीख रहे हो तो इसमें क्या है, बट फॉर्चुनेटली so many free resources are also available that one can do that. So this is what I've created. इसके बाद मेरा attitude है खुद जाके आप करें, जो कर सकेगा वो करेगा, and I personally hope that a few years from now we will see a few people doing very well who will say हमारी शुरुआत वहीं से हुई थी, हमने कुछ ऐसे पढ़ लिया था, वो कर लिया था, वो है। WhatsApp, हम वही WhatsApp, वो नहीं, भाई जूम वूम वगैरह। सी पीपल हैव अ मिस्टेकन नोशन दैट वो है, सी लर्निंग हैपेंस इनसाइड योर ब्रेन, वो टीचर की शक्ल देख के थोड़ी होती है। तो सो ये एंड मोस्ट ऑफ दिस विल बी क्यूरेटेड रिसोर्सेज, ये नहीं है कि मैं लेक्चर दे रहा हूँ, तो मोस्ट ऑफ दिस विल बी क्यूरेटेड। ओके, आपका कुछ कहने का मन कर? हाँ हाँ कोई डाउट नहीं, पर लेटर ही रियलाइज कि दकियानूसी लोग भी तो आपको मार डालेंगे पहले, फिर आप सो दिस इज द पॉइंट। बट हाँ नहीं, ये बहुत interesting thing is that although we are around for billions of years, quote unquote progressive humans are only 10 to 15,000 years since the agricultural age. 5,000 years since etc. Real progress is only after Galileo, Newton, etc. and very accelerated last 50 years. So that is why it is very interesting for people to speculate what the next 100 years are going to be like. अब ये सोचना कि अगर इवन इफ से 15,000 years पहले हम एग्रीकल्चर थे और हमने हंटर गैदरर से बदल के एग्रीकल्चर आए, अब से 15,000 years तक एक्सप्लोर अगर करोगे तो वी विल बी स्पेस फेयरर्स। मैं कई बार कहता हूँ, अब मैं बहुत कहा है लोगों से, मैंने कहा अब के जो बच्चे हैं ये सब लोग मून, मार्स, जुपिटर इस सब को अपना जैसा मानेंगे जैसे हम लोग अमेरिका, लंदन, यूरोप को कहते हैं। एंड बच्चे जो हैं दे विल गो टू द मून फॉर द हनीमून, दे विल गो टू जुपिटर फॉर द 25th सिल्वर जुबली ऑफ द वेडिंग एनिवर्सरी, वो सब। और अगर आप अभी देखो तो एलन मस्क वगैरह ने लो लेवल स्पेस फ्लाइट तो एज ए टूरिस्ट बना ही दिया है। तो मून, हाँ, so therefore what I am saying is many people believe that we will become a space, in fact very seriously, ये नील डिग्रास टाइसन का तो इसमें बहुत कुछ है। तो इसको कह रहे हैं टेराफॉर्मिंग मार्स। सो मार्स को लिवेबल बनाने के प्रोजेक्ट को टेराफॉर्मिंग मार्स कहते हैं। और नील डिग्रास टाइसन का कहना है कि आप टेक्निकली यू कैन डू इट, बट व्हाई डू इट, व्हाई नॉट टेराफॉर्म द अर्थ इटसेल्फ, व्हाई नॉट मेक द अर्थ इटसेल्फ बेटर। कहते जितनी जितनी प्रॉब्लम्स की वजह से यू वांट टू गो टू द मार्स, you solve that problem on the earth itself. So it's very interesting thing, but even imagining 100 years hence is extremely difficult for people, because the whole concept is just like you go back to the past. We are a generation who has seen from no electricity to electricity and see the big difference. And we are, can you imagine, this is one of my favorite stories, थोड़ा हिंदी भी बोल देता हूँ। ये बर्तन में कलई करने वाला, आप अपने बच्चों को समझा सकते हैं कि बर्तन में कलई करने वाला कोई है कि रुई की धुनाई करने वाला, बता सकते हो किसी को क्या होता है? अरे अब तो वो छोड़ो, वो स्याही की दवात होती थी और गीली स्याही होती थी, और एक दफ्तर में आदमी होता था जिसका काम था स्याही भरना हर जगह। मतलब you can't imagine that. So in a similar sense, we'll see many of these things. But I recall कि अब थोड़ा बीमार भी रहता हूँ, so I recall now हमारे ज़माने में जब छोटे थे ब्लड प्रेशर नापने के लिए एक डॉक्टर चाहिए होता था. वो ऐसे ऐसे का उसको स्फिग्मो मैनोमीटर कहते थे. वो एक आँख से देखता था मैनोमीटर कहाँ जा रहा है, एक कान से सुनता था आपकी वो कहाँ. आज हम ऐसे कुछ लगाते हैं सब बता देते हैं. एंड प्लस ऑटोमेटिक वाले भी हैं continuous. So it is, and especially after this quantum thing, so many things will happen. Large amount of data processing and capturing and processing will be done extremely fast. And the big thing is that there is a convergence now. So यही quantum से thermonuclear fusion से आपकी energy आ जाएगी. So it will be an unlimited energy supply kind of a situation. That is going to get agriculture. So अब आपको याद होगा ज़्यादा से 400 साल पहले मैल्थस ने कहा था हम सब भूखे मर जाएंगे. एक हाबर आया उसने कह दिया नहीं इतना खाना खाओगे कि ओबीस हो जाओगे. So we are going to have a very interesting thing, and this is, in fact, even this whole idea. So one of the things which I think is very important is for all of us from all religions, somehow it has been thrust in our mind that humans are the most superior thing. Logic says, where does evolution say that evolution has to stop with humans? मतलब हमने मान लिया कि हम सबसे श्रेष्ठ हैं, बट एवोल्यूशन की थ्योरी में तो कहीं नहीं दिखता है कि प्रोग्राम में लिखा है कि ह्यूमन के बाद स्टॉप करो. सो देयर विल क्लियरली बी एन एवोल्यूशन इनटू द नेक्स्ट काइंड ऑफ थिंग. हम जैसे वो बंदर और हमारे बीच में वो 93% तो डीएनए सेम है ना, वो जो 7% के डिफरेंस में हो गए. तो नील डिग्रास टाइसन ने कहीं कहा है, अभी आप इमेजिन करो कि एक और स्पीशीज़ है जिसका डीएनए हमसे वही 7% है और इंटेलिजेंस स्केल में आगे बढ़ गया, तो क्या होगा? उसको तो हम सब इंसान बेवकूफ़ लगेंगे, उसको तो एक स्टीफन हॉकिंग्स लगेगा कि ये थोड़ा ठीक सा है और कहेगा ये स्टीफन हॉकिंग ठीक है, ये एस्ट्रोफिजिक्स सब अपने सर में कर लेता है, वो मेरा टिमी आ रहा है अभी स्कूल से वो भी ये कर लेता है. See, we assume ये है, but there is no reason in biology to see, because we know it is all evolution and we have seen this evolution happen. तो कहाँ evolution में लिखा है कि बहुत सारे आइंस्टाइन टाइप नहीं हो सकते, बहुत सारे स्टीफन हॉकिंग नहीं हो सकते, आज वो रेयर है. तो मेरा एग्जाम्पल इसका है कि ज़्यादा दूर नहीं, कुछ ही समय पहले जब बिजली कड़कती थी और बिजली आती थी, इट वॉज अ रेयर ओकेजन. ये माइकल फैराडे, मैक्सवेल, इन लोगों ने मिलके उसको डेली का काम बना दिया कि जब चाहो बिजली बना लो. तो उसी तरीके से द लिमिट्स ऑफ इंटेलिजेंस दैट वी सी एज ह्यूमन इंटेलिजेंस इज टुडेज डेटा, एंड देयर इज नो गारंटी दैट इट विल रिमेन फॉर सो मच, एंड विद द प्रोग्रेस इट वुड डू मच मोर. एनीवे, सो इट इज इंटरेस्टिंग टू फैसिनेट. साइंस फिक्शन करो, ये करो, नया रिलीजन लॉन्च कर दो. हाँ, हम तो करें नहीं, लॉ नहीं है कोई यहाँ पे नया रिलीजन लॉन्च करने का. चलिए रमेश जी.
So thank you, sir. And if someone wants to say something for 1 or 2 minutes, then welcome. Otherwise, thank you for joining us. And let's have a group photograph. Then we'll close. Okay, thank you. Okay. I can share it on WhatsApp, but I have to remove the videos. Otherwise, because file size hai, I can put it in Google Drive and can share, then you can download with complete videos. Sure, I will share. Okay.